Hello there, and welcome to Science for Sleep, where curiosity curls up beside you and science takes its time. Tonight we're going to wander into one of the strangest regions of the universe. Not a cluster of brilliant galaxies, not the fiery nursery of newborn stars, but rather the opposite. A place so staggeringly large and so unsettlingly empty that astronomers gave it a name both simple and mysterious: the Booty's Void. Imagine an ocean where you expect islands, but instead you find a hollow basin stretching farther than your mind can easily hold. That is what we are drifting into tonight. But before we set off into that silence, let me ask you something. Where are you listening from right now? Is it evening for you, with a quiet room and perhaps a cup of something warm nearby? Or is it early morning, with sunlight beginning to brighten the edges of your day? The universe is vast enough that at this very moment, people scattered across countless time zones might be sharing this same thought with you. All of us tiny beings thinking about something as enormous and elusive as a cosmic void. There's something grounding in that, isn't there? A reminder that even as we talk about expanses billions of light years across, the experience of hearing about it happens here, now, in the small bubble of your own time and place. If this slow exploration feels like the kind of journey you want to bring into your nights more often, a like or a subscription helps this quiet corner of the internet reach others who might need it too. The universe is large enough for everyone to find a little patch of wonder before drifting off to sleep. So, let's settle in together. Ease into your pillow, let your breath slow, and picture this. You're looking at a map of the universe. Not a map of continents and oceans, but of galaxies, tens of billions of them. Normally the universe looks a little like a cosmic web, enormous strands of galaxies connected in filaments, creating a structure that reminds scientists of foam or lace, with dense clusters where galaxies huddle together and vast spaces in between. It's not smooth, not even. It has texture, rhythm, and complexity on the largest scales imaginable. And yet, right there in the northern constellation of Booties, scientists stumbled on something that looked almost wrong: a giant hole. When you first hear the phrase cosmic void, you might imagine pure nothingness, like an empty page or the blank screen before a video begins. But even space that looks empty usually has something, even if it's faint. A few scattered stars, thin wisps of gas, faint background radiation humming in the distance. In the Booty's Void, though, what startled astronomers was not just its existence but its scale. This wasn't a small bubble or an ordinary gap between clusters. This was a stretch of space about 330 million light-years across. To give you some sense of what that means, if our Milky Way galaxy sat in the middle of such a void, we would not have discovered other galaxies until the 1960s. For all of human history until then, the night sky would have appeared almost completely barren, sprinkled with only a few dim smudges rather than the thousands we can see. When it was first mapped in the early 1980s, researchers struggled with the idea. Astronomers Robert Kirshner and his team were charting the distribution of galaxies when they noticed the absence. It was like drawing a detailed picture of a forest, and suddenly hitting a vast clearing where no trees grew. They gave it a name, the Booty's Void, after the constellation in which it appears. But naming it didn't make it any less perplexing. The numbers implied that within that spherical volume of space, there should have been thousands upon thousands of galaxies. Instead, only a handful appeared. The human brain, evolved to walk through forests, rivers and villages, has trouble holding numbers this large. A light year alone, the distance light travels in a year, is about 9.5 trillion kilometers. Multiply that by hundreds of millions, and you begin to see the kind of scale involved. Yet even if you can imagine that distance, what unsettles scientists is the emptiness itself. The universe formed in a way that produced galaxies everywhere, spread along filaments and knots. So how can such a vast volume be missing so many of them? The Booty's Void is not completely devoid of matter. A small number of galaxies are adrift there, faint and lonely, cut off from the usual cosmic crowd. Imagine one small city sitting alone in the middle of a desert the size of entire continents. That is the situation of those galaxies. What kind of lives do they lead, if galaxies can be said to have lives? They rotate, form stars, and swirl in the dark just like others, but the neighbourhood is eerily empty. Few gravitational interactions with neighbours, few galactic collisions, little outside stimulation. Some scientists wonder whether galaxies in such environments evolve differently than those in busier regions. Asking why this void exists leads to deep questions about the formation of the cosmos itself. In the early universe, matter was spread nearly evenly, with tiny ripples imprinted in the cosmic microwave background. Over billions of years, gravity pulled matter together into the filaments and clusters we see today. But those same processes should leave behind voids where matter was less dense. The Booty's void, however, is larger than what those models comfortably predict. It is as though something pushed matter away more strongly here, or perhaps the initial conditions contained a particularly extreme fluctuation. Either way, studying it helps astronomers refine their understanding of cosmic structure formation. For us, sitting in our own galaxy with countless neighbours nearby, it's hard to imagine what the night sky of a planet inside such a void would look like. If you were standing on a hypothetical world orbiting a star within one of the few galaxies there, the sky might be shockingly dark. Instead of dozens of bright galaxies visible through telescopes, you might only see one or two faint smudges. It would be easy to conclude that your galaxy was alone in the universe. That thought alone can make the void feel eerie, not just empty but isolating. And yet, in some sense, the void is simply part of the tapestry. Just as the universe contains great walls and filaments, so too does it contain deserts and hollows. The Booty's void is the most famous example, but it is not unique. The cosmic web is full of voids, though most are smaller. Think of a sponge, full of holes, but still holding its shape. The Booty's void is one of the largest bubbles carved into that sponge. Its existence reminds us that the universe is not uniform. It is clumpy, textured, varied. And in that unevenness, we find questions that keep cosmologists awake. Why do some regions gather matter while others remain sparse? What does that distribution say about the fundamental laws that shaped everything after the Big Bang? When you stare into a void like Booty's, you're not just staring into emptiness. You're staring into a clue, a piece of the puzzle about how everything came to be arranged the way it is. The idea of emptiness also plays with the human imagination in ways that numbers alone cannot explain. For thousands of years, people looked at the night sky and saw it as infinite, full of stars without end. To find out that not only is it not infinite in the way we once thought, but that it contains pockets of true vast silence, is unsettling. It is like exploring a seemingly lush forest, only to find an enormous cavern within it, so large and dark that even sound seems reluctant to enter. And so, as we drift further into this great emptiness, we carry both the scientific questions and the emotional ones. What is it about nothingness that captures our attention so powerfully? Why do we find emptiness eerie, even when we're speaking about distances so great that no human will ever directly experience them? The Booty's void is not a danger to us. It is simply there, far away, a quirk of cosmic geography. And yet, to know it exists stirs something ancient inside us. The same curiosity that made our ancestors ask what lies beyond the horizon now pushes us to ask what hides in a darkness hundreds of millions of light years across. When astronomers first began drawing serious maps of the universe, their work resembled the careful sketching of ancient explorers. Early sailors charted coastlines, noting where harbours lay and where dangerous shallows lurked. They worked with incomplete information, filling in only what they could see, leaving broad blank spaces with the tantalizing words, "Here be dragons." In much the same way, astronomers in the 20th century were venturing into uncharted territory, though their maps were not of oceans but of galaxies. And into one of those maps appeared something stranger than any dragon, an enormous hole where galaxies were expected to be. In the late 1970s and early 1980s, technology was reaching a point where surveys of the sky could move beyond individual galaxies and begin tracing the grand architecture of the cosmos. Galaxies are not sprinkled randomly like sugar on a table. They clump and string together, forming patterns that stretch across unimaginable distances. Researchers wanted to know whether those patterns were consistent everywhere, or if they varied, and if so, why. One of the most influential surveys was led by Robert Kirshner and his colleagues at the University of Michigan. They aimed to measure redshifts, the stretching of light from galaxies as the universe expands. By carefully cataloguing these shifts, they could not only note where galaxies were on the sky, but how far away they were. With that information, the flat two-dimensional map of the night sky could suddenly become three-dimensional, showing not just where galaxies are located, but how they are arranged in depth. For the first time, humanity was beginning to peel back the curtain on the true large-scale structure of the universe. It was during one of these surveys in the region of the constellation Bootes that the unexpected appeared. As the data points were plotted, instead of a scatter of galaxies filling the space, there was a vast gap. On the page, it looked as though a large circle had been drawn and left uncoloured, a cosmic bubble devoid of nearly everything. At first, it was tempting to think it might be an artifact of incomplete data. Maybe the survey had missed galaxies in that region, or perhaps something in the instrumentation had skewed the results. But as more observations accumulated, the truth became unavoidable. There was genuinely an enormous volume of space where galaxies were shockingly scarce. Imagine working for months on a jigsaw puzzle, slowly piecing together thousands of fragments into a grand picture. Then, when you step back, you find a massive empty space in the middle where no pieces seem to fit. You check the box, count the pieces, and look under the couch. But no, the hole is real. That was the feeling when astronomers realized they had uncovered what would be called the Bootes void. The numbers made the discovery more striking. Based on the density of galaxies in surrounding space, astronomers expected tens of thousands of galaxies in that volume. Instead, they found only a few dozen. In a universe that seemed to thrive on abundance, this was a wilderness of scarcity. The announcement drew both excitement and puzzlement. Scientists love anomalies because they hint at deeper truths. If most regions of space are laced with galaxies and one region is not, then something in the history of the universe must explain why. Was it a natural outcome of cosmic evolution? Was there a hidden mechanism at work in the early universe that carved out such hollows? Or could it be that our theories of a large-scale structure needed refinement? At scientific conferences, the void became a topic of fascination. To some, it seemed like a statistical fluke, an extreme example of a natural pattern. The cosmic web is full of voids of different sizes after all. Why not one especially large one? To others, the Bootes void seemed too vast to be easily dismissed. It was, as one astronomer put it, a hole in the map of the universe, and holes beg to be explained. It's worth pausing to imagine how those first plots looked. Before digital visualizations and immersive computer models, astronomers used pen plots and early computer printouts. Dots represented galaxies, spreading across sheets of paper. Where galaxies clumped together, the page grew dense with marks. Where they thinned out, the paper was sparse. And then there, in the constellation Bootes, almost nothing. A blank region spanning hundreds of millions of light years. As more sophisticated surveys followed, the void remained. It was no illusion, no trick of incomplete data. Later work using larger telescopes and more comprehensive redshift catalogues confirmed its existence. And with confirmation came curiosity from the broader scientific community. What exactly was inside that hole? And what could its presence teach us about how the universe builds itself? Cosmologists began to run simulations of how matter clumps together over billions of years. In the early universe, slight differences in density acted like seeds. Where matter was denser, gravity pulled more in, creating clusters and filaments. where matter was less dense, gravity had less to work with, and those regions grew emptier over time. The result was a universe shaped like a web, strands of galaxies with voids in between. But even in those simulations, voids of the Bootes scale were unusual. It was as though the puzzle pieces had arranged themselves into a gap larger than the picture allowed. This raised another question. Could the void actually be multiple smaller voids strung together, giving the appearance of one giant hole? Some researchers proposed that what looked like a single enormous sphere of emptiness might instead be overlapping cavities, much like bubbles in foam that merge into larger pockets. Others argued that even if that were the case, the sheer scale still demanded explanation. Whether one void or many, the result was still a region hundreds of millions of light-years across with precious little inside. The human imagination, of course, did not stay silent. News of the Bootes void seeped beyond academic journals. Writers and science enthusiasts described it as the Great Nothing, a cosmic scar, even a possible hiding place for phenomena we had not yet understood. When people first read that a region 330 million light-years wide contained only a scattering of galaxies, the reaction was often visceral. It wasn't just numbers, it was the feeling of standing at the edge of a vast dark canyon and realizing the opposite side was so far away you might never see it. The void also sparked humorous speculation. If aliens wanted to build something enormous, perhaps a structure on scales beyond our comprehension, the Bootes void would give them room. Of course, such ideas are playful, but they point to something real in our psychology. Emptiness unsettles us. We are used to patterns, density, life fill in space. When faced with vast hollowness, our minds instinctively ask, why? Scientists, too, are not immune to that sense of unease, though they channel it into equations and models. The discovery of the Bootes void meant that any comprehensive theory of cosmic evolution had to account for such extremes. If the universe could produce such emptiness, then our models had to explain it. Over the decades, simulations have improved, and while such voids remain unusual, they are no longer inexplicable. Still, each new survey that maps the cosmic web returns to the Bootes void like a familiar scar, a reminder that the universe is not evenly generous in where it places its galaxies. From a technical perspective, charting such a void requires immense patience. Each galaxy's redshift must be measured individually, each data point logged, each one confirming the shape of the emptiness. The more data that came in, the more the outline of the void sharpened. It wasn't perfectly spherical, but close enough to appear as an enormous bubble in the cosmic foam. The galaxies that did exist inside it were like crumbs scattered in an otherwise empty bowl. To grasp the scale more viscerally, picture this. Our Milky Way is part of a cluster called the Local Group, and that group belongs to a larger structure, the Virgo supercluster. From Earth, with amateur telescopes, you can see hundreds of galaxies sprinkled across the sky. If our galaxy had been placed inside the Bootes void, though, those galaxies would simply not be there. To see another galaxy at all would require far larger telescopes, and even then, the view would be dim. In such an environment, the idea of being alone in the cosmos would not just be a philosophical worry, it would be an observational fact. This is what astronomers mean when they say the void is a hole in the map. It is not a hole in the sense of something artificial or torn, but in the sense of an absence where presence was expected. Like ancient cartographers who drew blank patches of ocean, modern astronomers confronted a blankness written in the language of galaxies. The difference is that instead of imagining sea monsters, they turned to physics, gravity, and the deep history of the cosmos for answers. Over time, the Bootes void became a benchmark. Any new simulation of cosmic structure had to reproduce not only the dense clusters and sweeping filaments, but also the cavernous voids. If a model could not generate such emptiness, it was incomplete. And so, in a quiet way, this hole in the map has shaped modern cosmology, forcing theories to reckon with the reality of scarcity as much as abundance. Yet for all its importance, the void remains oddly underdescribed in public imagination compared to galaxies, black holes, or supernovae. Perhaps it is harder to marvel at nothingness than at explosions of light. But in its silence, the Bootes void speaks volumes. It tells us that the universe is not simply full, but structured. It whispers that absence is as important as presence in shaping the cosmic web. It shows us that even in a universe of countless galaxies, there are still deserts so immense that human language strains to capture them. The hole in the map is not a mistake, not a gap in our data, but a reality written across hundreds of millions of light years. And as we gaze at it, we're invited to think not only about what is missing, but about what it means to live in a universe where missing pieces are part of the pattern. When we talk about the Bootes void today, it's easy to picture supercomputers humming in dim laboratories, digital sky surveys sweeping across billions of light years, and cosmologists working with immense data sets. But the first sense that something strange was lurking out there came not from advanced machines or sprawling observatories, but from a group of astronomers in the late 20th century who were simply trying to map the universe in more detail than anyone had done before. In truth, the earliest hints of cosmic structure go back much further, to centuries when the idea of even one other galaxy was still unthinkable. The road to discovering the void was paved by generations of astronomers asking what at first seemed like small questions. For most of human history, the night sky was seen as a dome sprinkled with stars. The idea that some of those faint smudges were island universes beyond our Milky Way did not become mainstream until the 1920s, when Edwin Hubble used the Hooker telescope at Mount Wilson to show that the Andromeda Nebula was not a nearby cloud of gas, but a galaxy in its own right. Millions of light years away, suddenly the universe grew dramatically larger. What had once been thought of as the entire cosmos, our Milky Way, was revealed to be one among billions. That discovery alone was enough to shake the foundations of how we think about our place in the universe. As the decades passed, astronomers became increasingly ambitious. Mapping the distribution of galaxies became the next great challenge. They wanted to know not just that galaxies existed, but how they were arranged on the larger scales. Were they scattered randomly like raindrops, or did they form patterns? By the mid-20th century, photographic plates and telescopes equipped with spectrographs were allowing teams to measure redshifts for hundreds and eventually thousands of galaxies. Each redshift was like a ticket stub from the expanding universe, telling astronomers how far away the galaxy was. Collect enough of them, and you could begin to build a three-dimensional map. In the 1970s, this mapping effort accelerated. Among the pioneers was Robert Kirshner, along with his colleagues Augustus Oehmler, Paul Schechter, and Stephen Schechtman. Their goal was deceptively simple: take a region of the sky and chart the galaxies within it in detail. The constellation Bootes, high in the northern sky, became one of their targets. They weren't expecting to find anything unusual. After all, by then it was already known that galaxies tended to clump into clusters and superclusters, with some voids between them. What they did not expect was the sheer scale of absence that greeted them. Imagine the painstaking work. Night after night they gathered spectra, measuring faint lines of light stretched by the universe's expansion. Each measurement placed a galaxy on the cosmic map, like pinning down a city on a globe. Over time, a pattern emerged. Clusters appeared, filaments extended, but then in one particular region, the dots grew sparse, then sparser still, until finally there were almost none. It was not just a small pocket of emptiness, it was an expanse hundreds of millions of light years across. At first, there was skepticism, even among the team themselves. Could it be that the survey had simply missed galaxies? Perhaps their instruments had not been sensitive enough, or perhaps dust obscured part of the sky. Errors are common in early mapping attempts, and caution is a habit deeply ingrained in scientists. But as they checked and rechecked, the gap persisted. More observations confirmed it. The void was not an illusion. it was real. The paper announcing the discovery came in 1981, and it landed with quiet weight in the field of cosmology. Here was a hole so large that it seemed to challenge the very notion of how matter should be distributed in the universe. The Bootes void, as it came to be called, instantly joined the lexicon of cosmic structures. For many, it was a reminder that we were only just beginning to glimpse the true complexity of the cosmic web. But it's worth appreciating how bold this discovery was at the time. The idea of voids was not new. Smaller gaps between clusters had been noted before, but nothing of this magnitude had ever been documented. To claim that such an enormous portion of the universe was almost empty was, in a sense, daring. It required not only careful data, but the willingness to stand by results that seemed almost absurd. After all, how could something so large exist and yet remain unseen until then? The answer lies partly in the difficulty of the task. Mapping galaxies across 3 dimensions requires enormous effort. A 2-dimensional image of the night sky doesn't reveal distance. Galaxies that appear side by side may be separated by hundreds of millions of light years. To detect a void, you need depth, and to get depth, you need redshift measurements. Each one is time-consuming to obtain. That's why it took until the late 20th century for astronomers to have enough data to notice such vast patterns. Even so, once the Bootes void was identified, it raised eyebrows. One well-known astronomer, upon hearing about its size, quipped that if our Milky Way were inside it, we might never have discovered other galaxies at all. The scale of the emptiness was that profound. In some ways, the discovery made the universe feel even larger, not because it added new galaxies, but because it revealed how unevenly they are spread. It's also important to remember that this was happening during a time of major shifts in cosmology. The 1970s and 1980s were decades when theories about dark matter were gaining traction, when inflationary cosmology was being developed to explain the structure of the early universe, and when computers were finally becoming powerful enough to simulate galaxy formation on large scales. The Bootes void arrived as a real-world puzzle that these new ideas would have to account for. It wasn't just a curiosity, it was a test. Any model of how the cosmos evolved would need to explain why such an enormous region could be so sparsely populated. The astronomers themselves, though, likely felt a mix of excitement and trepidation. To stumble on something so unexpected is thrilling, but it also invites scrutiny. Were they sure? Could they defend their results? In the careful language of scientific papers, they laid out the evidence, and as other teams followed up with their own surveys, the void was confirmed again and again. Eventually it became one of the most famous features in the map of the universe, a kind of landmark of absence. But before we move too quickly past this moment, it's worth imagining what it must have been like in those early nights at the observatory. A handful of astronomers, bundled against the cold, guiding telescopes toward faint smudges of light, carefully recording spectra on photographic plates. The sky above them stretching endlessly, while on the paper in front of them, the data slowly drew an outline of something that wasn't there. Discovery is often portrayed as a sudden moment, a eureka, but more often it is gradual, a creeping realization, a sense that the pattern emerging is stranger than expected, that the data are whispering something new. For Kirshner and his team, that whisper grew louder until it could no longer be ignored. The absence itself became the story. In science, we often focus on what is present, the star that flares, the planet that orbits, the galaxy that shines. But here was a case where the absence of those things carried equal weight. The blank space on the map was as meaningful as the dots that filled the rest. It's a reminder that science progresses not only by cataloguing abundance, but by recognizing where there is scarcity. The dog that didn't bark, as the old detective phrase goes, can sometimes be the most important clue. And so, the Bootes void entered the scientific imagination, not as a singular oddity, but as a window into the processes that shape the universe. From then on, Every survey that extended farther and deeper into space included it, like an old landmark you check on the way to new discoveries. Astronomers wanted to know, was it unique? Were there others like it? How common were such voids, and what role did they play in the cosmic architecture? The answers would take decades of further work. But the first astronomers to notice the absence did something crucial. They pointed to the blank spot and said, "Here is something that needs explaining." They turned nothing into a scientific object, emptiness into evidence. And in doing so, they expanded not just the map of the universe, but the scope of human curiosity. It's easy now, with our massive computer simulations and galaxy catalogues containing millions of entries, to see the Boots void as just one part of a grander picture. But at the moment of its discovery, it was singular, unsettling, and strangely beautiful. A testament to the persistence of a few astronomers who were willing to spend countless nights chasing faint light across the sky, only to find themselves staring at the silence between. When astronomers first mapped the Bootes void in detail, the shock was not just in seeing the emptiness itself, but in realizing how profoundly it seemed to defy expectations. The universe, as far as scientists understood it, should not produce gaps of that magnitude very easily. On the scales we're talking about, hundreds of millions of light years across, matter tends to distribute itself in patterns that leave gaps, yes, but not normally this wide, not this stark. The void was not simply an empty spot. It was an empty spot that forced everyone to rethink how galaxies form and how matter organises itself over cosmic history. The problem begins with the basic picture of the early universe. Not long after the Big Bang, about 380,000 years later, the universe had cooled enough for atoms to form, and light could finally travel freely. That ancient light still lingers today as the cosmic microwave background, a faint afterglow stretched across the sky. When scientists study it carefully, they see tiny fluctuations in temperature and density, slight ripples where matter was just a little more or less concentrated than average. Those ripples are the seeds of everything we see today: galaxies, clusters, superclusters. Gravity would slowly pull the denser regions into even denser clumps, while emptier regions would expand into voids. From this picture, you might expect a cosmic web, a network of filaments and clusters woven together with empty bubbles in between, and indeed, that's exactly what large-scale surveys show. But here is the catch. Simulations of this process, especially those using the laws of physics as we understand them, predict voids of certain sizes. Most are tens of millions of light-years wide, perhaps stretching to 100 or a bit more. The Bootes void, at over 300 million light-years across, is much larger than the typical outcome. It isn't just an outlier, it's an outlier among outliers. It's like rolling a die and getting the same impossible number over and over again. This is why astronomers sometimes say that the universe shouldn't have gaps this big. Not because it is impossible, but because it strains the probabilities. It pushes against the limits of what our theories comfortably allow. If you were to run the universe forward in a computer simulation 1,000 times, you might get something like the Bootes void once, maybe twice. But we are living in one of those rare outcomes, and that means either we've gotten lucky, or there's something missing in the way we understand cosmic structure. Another way to put it is this: the universe is clumpy, but it shouldn't be this uneven. Think about mixing cream into coffee. At first you see streaks, swirls, and patches of different density. Given enough time though, it all evens out into a fairly uniform drink. In the universe, gravity is constantly stirring the pot, pulling matter together, shaping filaments. Voids form naturally, but over time, they usually don't grow beyond certain limits, because other structures collapse and tug matter inward. To end up with a cavity as massive as the Bootes void, you'd need an especially extreme region in the early universe, a place that was underdense enough that gravity simply couldn't compete. The implications ripple out in several directions. One is that such a void might help constrain our understanding of dark matter. Dark matter, the invisible mass that makes up most of the matter in the universe, plays a critical role in galaxy formation. It provides the gravitational scaffolding around which galaxies cluster. If voids are too large, maybe that suggests dark matter behaves slightly differently than we think. Or perhaps it hints that our models of how dark matter and ordinary matter interact need to be fine-tuned. Another possibility involves the concept of cosmic inflation. Inflation is the idea that in the earliest fractions of a second after the Big Bang, the universe expanded faster than the speed of light, stretching tiny quantum fluctuations into cosmic-scale ripples. These ripples became the seeds for structure. But if inflation produced regions that were unusually underdense, perhaps that could explain why a void as large as Bootes exists. In other words, maybe the void is a fossil of some quirk in the inflationary era, a fingerprint from the first instant of time. From the perspective of human intuition, though, the void feels more like a violation of symmetry. Our brains expect some level of balance. When you toss marbles into a box, they don't usually all avoid one corner. When you plant seeds in a field, you don't normally get a giant patch of bare ground unless something unusual happens. The Bootes void is like that bare patch. Not impossible, but peculiar enough to demand explanation. It is the kind of result that makes scientists sit up and re-examine their assumptions. The rarity of such voids also means they serve as excellent laboratories for testing cosmological theories. By comparing the actual distribution of galaxies inside the void with the predictions of simulations, astronomers can probe the accuracy of their models. Do the galaxies we find inside the void have unusual properties? Are they smaller, dimmer, or shaped differently than their cousins in denser regions? Do they form stars at different rates? Each answer gives a clue to how voids evolve. But let's return for a moment to the visceral reaction many had when the void was first described. If the universe is meant to be filled with galaxies, why does this enormous dark bubble exist at all? To the casual reader, it almost sounded like a mistake, as if the universe had forgotten to paint in that part of the canvas. That sense of wrongness is precisely what makes it so fascinating. It challenges not just our science, but our psychology. We are creatures who evolved to expect regularity. Rivers flow downhill, apples fall when dropped, forests spread evenly unless cut back. Emptiness on this scale feels alien, even though it is part of the natural order of things. It's also a reminder that our sense of what the universe should be like is often built on incomplete understanding. Before the discovery of other galaxies, people thought the Milky Way was the entire cosmos. Before we measured the expansion of the universe, people thought it was static. Each time, reality proved larger, stranger, and less symmetrical than expected. The Bootes void is one more step in that tradition, a reminder that the universe doesn't answer to our intuitions. Still, scientists resist shrugging off anomalies. If the void is unusually large, that tells us something. It may tell us about the statistical extremes of cosmic structure, or it may point to new physics. Either way, ignoring it would mean ignoring a clue. And in cosmology, clues are precious. Consider also the role of voids in shaping the universe at large. Voids are not just empty spaces, they influence how matter moves. Galaxies on the edges of voids feel less gravitational pull from within, and more from without, so they tend to stream outward, enhancing the void's emptiness over time. In that sense, voids can grow larger as they push matter away. But even with that mechanism, it is hard to grow something as large as Bootes. The fact that it exists suggests that the interplay of gravity, expansion, and initial conditions can sometimes combine to produce extraordinary results. This raises a philosophical question as well. When we say the universe shouldn't have gaps this big, what do we really mean? We mean that according to our current models, such gaps are improbable, but improbable things do happen. Toss a coin 1,000 times, and somewhere in that sequence you may well get 10 heads in a row. It doesn't break the laws of probability, it simply illustrates that extremes occur. The Booty's void may be one of those extremes, a cosmic coin toss that landed in an unusual way. Yet improbability and impossibility are not the same. The fact that the void exists means it must be possible, and that alone forces scientists to expand their thinking. If our models cannot easily produce it, perhaps the models are incomplete. That tension between improbability and reality is what drives progress. Every time nature surprises us, it nudges us closer to a more accurate description of reality. Another reason the Booty's void commands attention is its loneliness. Most voids are not completely empty. They contain faint galaxies, stray clouds of gas, maybe even filaments too thin to detect easily. The Booty's void does too, but far fewer than expected. If you lived in one of those galaxies, the sky would look profoundly different. The vast majority of other galaxies would be so distant and faint as to be invisible without advanced telescopes. In a sense, such a perspective dramatizes the question of why the universe looks the way it does. Why are some neighborhoods bustling while others are nearly deserted? The answer may ultimately lie in randomness layered over laws. Gravity pulls matter together, but where that matter starts off matters greatly. If the early universe happened to have a patch that was underdense, then billions of years later we get a void. It is lawful randomness, order emerging from chaos but still allowing for extremes. The Booty's void is not a glitch. It is a reminder of the variety that natural processes can produce. Still, that doesn't make it less unsettling. For those who first saw the data, the sense of encountering something that shouldn't be there was unforgettable. Even now, the void carries that aura. It is both an expected consequence of physics and an extreme that makes us question physics. It is simultaneously ordinary and extraordinary, like a desert so large that you wonder whether you're still on the same planet. So why shouldn't the universe have gaps this big? Because according to our neatest, cleanest models, it shouldn't, and yet it does. And therein lies the beauty of science. When faced with reality, we must adjust the models, not the other way around. The void doesn't answer to our expectations, it simply exists, silent, immense, and unyielding. And as we try to explain it, we find ourselves learning not only about the fabric of the cosmos, but about the limits of our own imagination. If the universe can carve a hole 300 million light-years wide, then what else might it do that we haven't even begun to consider? When we shift our attention from the vast emptiness of the Booty's void to the galaxies themselves, the contrast is almost overwhelming. On one side of the picture, there is silence stretched across hundreds of millions of light-years. On the other, there are the galaxies that populate the universe like glowing archipelagos, each one a gravitationally bound system of stars, gas, dust, and dark matter. To think of galaxies as islands in a cosmic sea is not just poetic flourish. It is a fitting description of the way they are distributed, scattered across an ocean of space, where the water is invisible but very real. And when we consider a void like Booty's, the metaphor becomes even sharper, because there the sea seems almost empty, with only a few lonely islands breaking the surface. Each galaxy is a microcosm. Our own Milky Way contains perhaps 400 billion stars, along with countless planets, asteroids, and clouds of interstellar gas. It is held together by gravity, much of it contributed by dark matter, which forms an invisible halo around the galaxy. Spiral arms curl outward, rich with star-forming regions, while the core hosts a supermassive black hole. To us it feels immense, a universe in its own right. Yet when you zoom out far enough to see the larger distribution of galaxies, the Milky Way becomes just another speck among billions. The cosmic web, revealed by surveys that map galaxies across vast distances, shows this distribution clearly. Galaxies cluster into filaments and sheets, with voids between them. The result is strikingly reminiscent of foam or lace, where dense regions are connected by thin threads and empty bubbles fill the gaps. Within this structure, galaxies are like glowing beads threaded along filaments, lighting up the cosmic scaffolding. The Bootes void is one of the largest bubbles in this foam, and the galaxies inside it are the rare exceptions, islands marooned in an ocean of almost pure nothing. This perspective forces us to think of galaxies not as solitary objects, but as part of a larger ecosystem. Just as islands are shaped by the sea around them, galaxies are shaped by their cosmic environment. In dense clusters, galaxies interact frequently, tugging on one another with gravity, colliding, merging, stripping gas. Such interactions fuel bursts of star formation, transform shapes, and sometimes awaken dormant black holes. In contrast, galaxies inside voids live quieter lives. With fewer neighbours, they evolve more slowly, less disturbed by external forces. This difference makes void galaxies valuable to astronomers. They offer a glimpse of galactic evolution in relative isolation. The loneliness of such galaxies is hard to overstate. Imagine a civilization inside one, developing astronomy and looking outward. Their sky would hold stars just like ours, but when they built telescopes and searched for other galaxies, the view would be stark. Where we see the Andromeda Galaxy shining faintly but distinctly, they might see nothing at all. Where our deep sky photographs reveal hundreds of galaxies scattered across a single image, their photographs might show only a few faint smudges, distant and barely perceptible. The conclusion would be inescapable. They were alone in the universe. Only with extraordinary effort, building telescopes unimaginably sensitive, could they detect the faint traces of others. The psychological impact of such emptiness is difficult to imagine. For us, the crowded sky is a comfort. For them, the void would be the defining feature of reality. This analogy to islands also reminds us of the limits of travel. In human history, islands separated by vast oceans posed enormous challenges. Journeys across them were rare, dangerous and isolating. Galaxies face the same obstacle on a cosmic scale. The distances between them are so vast that even travelling at the speed of light, it would take millions of years to cross from one to another. Within clusters, where galaxies are relatively close, these separations are measured in tens of millions of light years, but inside voids the separations stretch much farther. The galaxies are like distant atolls in an endless ocean, forever cut off from one another. For any civilization that might arise, the stars within their galaxy would be reachable in principle, but the broader universe would be out of reach, locked behind a sea too wide to cross. From a scientific perspective, studying galaxies as islands highlights the role of dark matter in shaping the sea itself. The cosmic web is not formed primarily by the visible matter we see in stars, but by the distribution of dark matter, which outweighs ordinary matter by a factor of 5 to 1. Dark matter collapses under its own gravity into filaments, and galaxies form along these filaments like cities along trade routes. In this sense, the islands are not random. They are positioned by the invisible currents of dark matter that flow beneath the surface. When we look at a galaxy, we're really looking at the crest of a much larger structure, the luminous peak of an unseen mass that extends far beyond what telescopes can detect. This idea of galaxies as islands also emphasizes just how rarefied the universe really is. The spaces between stars within a galaxy are enormous, but the spaces between galaxies are exponentially greater. If the Milky Way were shrunk to the size of a dinner plate, the nearest large galaxy, Andromeda, would be several meters away. And that is in a relatively crowded region of space. Inside a void like Bootes, the distances between galaxies would stretch much farther still, making the ocean analogy feel all the more apt. The sea is not just wide, it is practically endless. And yet, despite their isolation, the galaxies in voids are not fundamentally different. They still form stars, harbour black holes, and rotate under the influence of dark matter. Some may be smaller or fainter, perhaps because the lack of interaction slows their growth. But in essence, they are still islands in the same sea, following the same basic laws of physics. Their isolation does not exempt them from the universal story. it simply gives them a quieter version of it. Astronomers have even used void galaxies to test cosmological theories. Because they are less influenced by outside forces, their properties can be compared more directly to models of how galaxies form. For example, some studies have shown that void galaxies tend to have more gas relative to their mass, perhaps because they are less likely to have had that gas stripped away by neighbours. They may also retain more of their original angular momentum, spinning in ways that reveal subtle clues about their early history. Each lonely island is like a laboratory, offering clean conditions for studying processes that are messier in crowded environments. When we look at the larger cosmic map, we see not just islands but continents. Clusters of galaxies, superclusters and walls stretch for hundreds of millions of light years, forming massive interconnected structures. Between them lie the voids, the dark oceans. The Bootes Void is one of the largest seas, a vast stretch with only a few islands scattered across it. To picture it is to imagine an archipelago so sparse that a sailor could travel for months without sighting land, each sighting a miracle of survival. In this way, the void is not just an absence but a reminder of the fragility of presence. That a few galaxies exist there at all is remarkable, like lone lighthouses on a stormy coast. It also reminds us of our own place. The Milky Way is not inside a void, but within a filament, part of a relatively crowded region. That is why our sky is rich with galaxies. But had we been placed in a void, our understanding of the universe would have been profoundly different. We might still be debating whether other galaxies existed at all. We might still believe ourselves the sole island in an empty sea. The fact that we were born in a crowded archipelago is, in a way, a stroke of cosmic luck. It gave us the data to discover the universe as we now know it. The metaphor of islands is not just a convenience. It captures something essential about the human experience of the cosmos. We are used to seas, to journeys, to exploration across difficult expanses. When we describe galaxies as islands in space, we are linking the incomprehensible to something familiar, and in that familiarity we find both wonder and humility. The universe may be vast beyond measure, but its patterns still echo the patterns we know. Clusters and voids, islands and oceans, presences and absences. Inside the Bootes Void, those echoes are stretched to their limits. The ocean grows so wide that the islands are almost invisible. The sea becomes the dominant feature, the emptiness overwhelming the presence, and yet, even there, the islands persist. Small, scattered, lonely perhaps, but real. They remind us that even in the greatest deserts of the cosmos there is something. Even in the most improbable gaps the story of galaxies continues, and so, when we think of the Bootes Void, we should not picture it as pure nothingness. It is not a perfect whole. It is a vast, dark ocean with a few isolated islands, glowing faintly in the distance. It is a reminder that even in absence, presence endures. The islands may be far apart, but they are still part of the same sea, still governed by the same currents, still part of the same cosmic map. When you first hear that the Bootes Void stretches across 330 million light-years, the number is so large that it almost deflects meaning. It is like being told that an ocean is 10 trillion litres deep, or that a mountain weighs several quadrillion tons. The human brain, evolved to count days, to track harvests, to measure journeys in steps and miles, is not built for these kinds of numbers. So to grasp the scale of the Bootes Void, we have to slow down, translate it into comparisons, and let the imagination gradually expand outward until something begins to click. A light year is the distance light travels in 1 year, about 9.5 trillion kilometres. Light, the fastest thing in the universe, which zips from the sun to Earth in just over 8 minutes, would need 330 million years to cross from one end of the Bootes Void to the other. That is older than many species of dinosaurs, older than entire geological eras on Earth. If you were somehow able to ride a beam of light starting at one edge of the void, you would not reach the other side until long after human beings, and perhaps even our planet itself, had passed from existence. To give another perspective, Our Milky Way galaxy is about 100,000 light-years across. The Booty's void could fit over 3,000 Milky Ways lined up side by side across its diameter. Imagine taking our entire galaxy, with its hundreds of billions of stars and countless planets, and repeating it not just once or twice, but thousands of times in a line. That line would only begin to span the emptiness of the void. And remember, that is just one dimension. The void extends in all directions, a roughly spherical bubble. To fill it with Milky Ways, you would need millions upon millions, yet instead of being filled, it holds only a few dozen galaxies scattered thinly like crumbs in a vast dark bowl. Astronomers sometimes compare the scale of the void to the observable universe as a whole. The observable universe has a diameter of about 93 billion light-years. By that measure, the Booty's void takes up only a fraction, but even that fraction is staggering. It is as though you zoomed in on a small patch of the Earth's surface and discovered an empty desert the size of entire continents. In a universe rich with galaxies, finding such a stretch of near-nothingness feels both improbable and sobering. Another way to understand the scale is to compare it to human history. Modern humans, Homo sapiens, have existed for about 300,000 years. Civilization, agriculture, writing, cities, all of it compressed into about 10,000 years. Compare that with 330 million years, the time it would take light to cross the void, when the first amphibians crawled onto land, when lush forests of giant ferns spread across ancient continents, when insects first grew wings. Light starting at one side of the Boot's void would only now be reaching the other. The scale does not just dwarf human history, it dwarfs Earth's biological history. It also dwarfs the scale of our explorations. The farthest human-made object, Voyager 1, has been travelling for nearly half a century and has reached about 22 light-hours from Earth. That is less than a single light day, let alone a light year. To compare Voyager's journey to the span of the Boot's void is like comparing the distance from your fingertip to a single grain of dust in the room. The void is so large that even our most ambitious machines, even the speed of light itself, cannot make it feel real in the terms we're used to. When scientists say the void is 330 million light-years wide, they are describing it conservatively. Some measurements suggest the effective diameter may be even greater depending on how you define its boundaries. Unlike a planet or a star, it does not have a clear edge. It fades gradually, from regions of almost total emptiness to regions where galaxies begin to appear more often. Defining where the void ends and the cosmic web resumes is part of the challenge, but even the lowest estimates make it one of the largest structures or anti-structures ever documented. This raises an interesting point. When something is so large, does it even make sense to call it an object? The Booty's void is not a physical body like a star or a planet. It is not a thing you could point to in the same way you point to the moon. It is an absence defined by what is missing. Its scale is measured by the galaxies that are not there. In that sense, it is less like a mountain and more like a canyon. And just as the Grand Canyon awes us by showing how much rock has been carved away, the Booty's void awes us by showing how little matter ever gathered there. The sheer size also alters how we think about cosmic structure. Galaxies are not just scattered individually, they form filaments, walls, and clusters. The largest of these structures stretch across hundreds of millions of light-years. The Sloan Great Wall, for example, spans about 1.4 billion light-years. Compared to that, the Boot's void is smaller, but still one of the largest voids known. If walls and filaments are the continents of the cosmic web, then voids like Booty's are the oceans. Together, they make up the full geography of the universe. Without voids, the web would not exist. They are not accidents, but integral parts of the structure. Their enormous scale is part of the balance, and yet the Booty's void stands out. Most voids are smaller, shallower, less stark. This one is like an ocean that seems to stretch farther than the horizon, an expanse so broad that even seasoned cosmologists pause when describing it. Its scale is not just impressive, It is troubling in the sense that it challenges statistical expectations. It is like finding a desert larger than any weather patterns can easily explain. When faced with something so big, we are forced to reconsider our models, our probabilities, our sense of what is normal. To bring the scale closer to human terms, consider this. If our galaxy were inside the boot's void, and if our ancestors had built telescopes centuries ago, the night sky would have looked profoundly different. Galileo's first telescope revealed countless stars and faint nebulae. Later, astronomers with improved instruments began to see galaxies beyond our own. But if they had been observing from inside the void, they would have seen far fewer of them. The deep sky photographs we now treasure, filled with swirls and smudges of distant galaxies, would have been almost empty. It might have taken until the late 20th century, perhaps even later, for anyone to confirm that galaxies exist at all. The scale of the void is not just spatial, it is experiential. It would change how an intelligent species understands its universe. This thought experiment also emphasizes how fortunate we are. The Milky Way sits in a relatively dense region, part of a filament rich with galaxies. This gave us a window into the wider cosmos much earlier in our history. From the perspective of scale, that was a cosmic gift. Had we been inside a void, the journey of discovery would have been delayed, perhaps by centuries or even millennia. The void's size would have hidden the truth. Astronomers sometimes visualize scale by compressing distances into more familiar terms. Imagine the observable universe shrunk down to the size of the Earth. In that model, the Booty's void would be about the size of a small continent, perhaps Australia, carved out of the surface. It would be a recognizable feature on the globe, something you could not miss. That is how large it is compared to everything else. The enormity of the void also makes it useful as a test of cosmology. When simulations try to recreate the universe, they must be able to produce voids of comparable size. If they cannot, then something is wrong. In that way, the void is like a benchmark, a measure of scale that theories must match. Its existence is a constraint, a way of saying, any successful model of the cosmos must allow for this much emptiness. At the same time, the void scale stirs emotions. People who hear about it often describe a sense of vertigo, as though looking over the edge of a cliff too high to comprehend. The emptiness becomes personal, a reminder of how small we are. Yet others describe it as comforting, a vast silence that puts human concerns into perspective. The scale of the void is so immense that it dwarfs not just us but our entire planet, our solar system, even our galaxy. In that humbling perspective, some find peace. It also opens doors for philosophical reflection. If the void is so large, does it suggest that absence is as fundamental as presence? That the universe is not just a collection of galaxies, but also a collection of gaps between them? The scale forces us to consider nothingness as a participant in the cosmic story, not just a background. The Booty's void is not an error or a flaw. It is part of the universe's architecture, its scale a natural counterbalance to the crowded filaments and clusters. But still, the numbers are difficult to digest. 330 million light-years. Millions of Milky Ways could fit inside it. A beam of light taking longer to cross it than the age of mammals on Earth. These comparisons only begin to touch its vastness. To truly feel its scale is perhaps impossible. We can measure it, describe it, simulate it. But to comprehend it fully is beyond us. And maybe that is the point. The Booty's void exists not only as a scientific object, but as a reminder of the limits of human imagination. Its scale is both a number and a challenge, a number we can write down, and a challenge to our ability to grasp what it really means. And so, when we talk about the Boot's void, we're not only talking about galaxies missing from a region of space, we are talking about scale itself. The kind of scale that bends the mind, forces analogies, and humbles our sense of significance. The void is not just an emptiness. It is a measure of how vast the universe can be, how extreme its contrasts, how far reality can stretch beyond our expectations. When you look at the Booty's void in the context of the universe as a whole, it doesn't sit there in isolation. It is one part of an intricate web that stretches across the cosmos, a pattern of matter on the largest scales imaginable. The void is striking because of its emptiness, but its meaning becomes clearer only when we compare it to what surrounds it. The walls of galaxies, the filaments that connect them, and the sprawling deserts of space in between. Together, these structures form what cosmologists call the cosmic web, the grand architecture of the universe. To picture this, imagine you are looking at a sponge under a microscope. You see networks of interconnected tunnels and cavities with thicker walls separating them. Or think of soap bubbles clustering together. Each bubble has thin boundaries where it touches others, and the space inside is hollow. The cosmic web works in a similar way. Filaments of galaxies and clusters form the boundaries, while the interior spaces are voids. The Booty's void is one of those interior spaces, but unusually large, like a bubble that grew far bigger than its neighbours. Filaments are among the most common features of this web. They stretch like bridges between clusters, narrow but immensely long, sometimes hundreds of millions of light years in extent. Galaxies along filaments are not evenly distributed, but tend to clump into knots where the filaments intersect. These knots become clusters and superclusters, some of the densest regions in the universe. The filaments serve as cosmic highways, channels through which matter flows, guided by the underlying distribution of dark matter. Walls are thicker structures, sheets of galaxies spanning vast distances. They form when multiple filaments intersect and spread out into broad plains. One famous example is the Sloan Great Wall, discovered in 2003, which stretches about 1.4 billion light-years across. It is one of the largest known structures in the observable universe, a sweeping continent of galaxies in the midst of the cosmic sea. Compared to such a wall, the Booty's void is like an adjacent ocean, a dark gulf pressing against the shoreline of galaxies. Then there are the deserts, the more ordinary voids scattered throughout the cosmic web. These are the in-between spaces, the hollows left when matter collects into filaments and walls. Most voids are relatively modest, tens of millions of light-years across, large enough to be staggering by human standards but small in the cosmic context. The Booty's void, by contrast, is a desert that seems to go on forever, dwarfing its neighbours and defying easy categorization. What is fascinating is how these different structures complement one another. You cannot have walls without voids, filaments without gaps. The cosmic web is a balance between abundance and absence, matter and emptiness. Each part defines the other. The Booty's void might seem unusual in its scale, but it is still part of this larger pattern. Its size only emphasizes the contrast. Comparing these structures also reveals the role of gravity and dark matter. Filaments form where dark matter has collapsed into long threads, pulling ordinary matter along with it. Walls form where multiple filaments converge, creating denser regions. Voids, in turn, expand as matter flows outward into the filaments. Over billions of years, this process amplifies the contrast, making filaments denser and voids emptier. The Booty's void is simply an extreme version of this cycle, a place where the balance tipped heavily toward emptiness. For astronomers, mapping these structures is like drawing the world's largest geography lesson. Instead of continents, rivers and mountains, they chart filaments, walls, and voids. Each survey adds new detail, revealing that the universe is not random but patterned, not uniform but richly textured. When they look at the cosmic web in 3 dimensions, it almost resembles a neural network, with galaxies glowing like synapses connected by threads of light. The voids are the dark gaps between, silent but essential. Comparisons also help to convey just how large and varied these structures are. The local group, our immediate galactic neighbourhood, is about 10 million light-years across. The Virgo supercluster, which contains the local group, spans about 110 million light-years. The Sloan Great Wall, as mentioned, reaches 1.4 billion. And then there is the Bootes Void, sitting at 330 million light-years, empty compared to its peers. Each of these numbers stacks upon the other, creating a hierarchy of scale that stretches the imagination. In many ways, the cosmic web is the natural outcome of the laws of physics. Gravity pulls matter together, dark energy drives expansion, and the interplay between them creates a universe that is clumpy rather than smooth. But within this predictable framework, extremes emerge. Some filaments grow longer, some walls thicker, some voids larger. The Bootes Void is an extreme void, just as the Sloan Great Wall is an extreme wall. Together they illustrate the range of what the universe can produce. There is also a practical side to these comparisons. By studying galaxies in filaments, walls and voids, astronomers can see how environment shapes evolution. Galaxies in walls and clusters are often elliptical, older, redder, having used up their gas in bursts of star formation triggered by collisions. Galaxies in filaments are more varied, some still actively forming stars, others more quiescent. Void galaxies, as mentioned earlier, tend to be bluer, with more gas evolving more gently. The contrast is striking, like comparing cities, towns, and isolated villages. Each has its own rhythm, shaped by its surroundings. The metaphor of deserts is particularly apt for voids. Just as deserts on Earth are not entirely empty but sparse and extreme, cosmic voids are not absolute nothingness but regions of scarcity. Life in a desert is shaped by its harshness, and galaxies in voids are shaped by their isolation. They may survive, even thrive in their own way, but their evolution is slower, less influenced by neighbours. The Bootes Void, as the largest desert, pushes this analogy to its limit. It is like the Sahara of the cosmos, a vast expanse where the rare oases of galaxies stand out all the more vividly. Another way to compare these structures is through their discovery. Clusters and filaments were easier to identify because they contain so many galaxies. They stand out in surveys like bright streaks on a map. Voids, by contrast, are harder to see because they are defined by absence. You have to map enough galaxies to realise where they aren't. It is like trying to notice silence in a room full of noise. You only recognise it when enough of the sound falls away. The Bootes Void was one of the first times astronomers realised just how loud that silence could be. Even today, when computer simulations recreate the cosmic web, scientists use comparisons between filaments, walls, and voids to test their accuracy. If the simulations produce too few voids or walls that are too short, something is missing in the physics. If they produce voids as large as Bootes too easily, something else is off. The universe gives us these benchmarks, and the comparisons are how we refine our models. From a broader perspective, these structures remind us that the universe is not a featureless expanse. It has architecture, a kind of skeleton revealed by galaxies. Just as the continents and oceans give Earth its shape, filaments and voids give the cosmos its character. The Bootes Void is one extreme feature of this landscape, a reminder that deserts can be as defining as mountains. And in reflecting on these comparisons, we also reflect on ourselves. The metaphors we use, islands, seas, deserts, walls, come from our own world, our own history of exploration. They help us make sense of scales far beyond our direct experience. By calling galaxies islands, voids deserts, and filaments highways, we bring the incomprehensible closer to home. In doing so, we create a bridge between human imagination and cosmic reality. So when we place the Bootes Void next to the Sloan Great Wall, when we compare it to filaments stretching across the sky, or to smaller voids dotting the cosmic map, we see not just numbers, but relationships. The void is vast, yes, but it is part of a larger balance, a universe that thrives on contrast. Without walls, there would be no voids. Without voids, no walls. Each defines the other, and together they create the cosmic web. The Buddha's void, then, is not an anomaly floating alone. It is a desert set against continents, a silence that makes the sound of galaxies more vivid. And in comparing these structures, we come closer to understanding the universe not as random chaos, but as a patterned whole, a tapestry woven from both presence and absence. When astronomers first realized the Boot's void was real, and not just an artifact of incomplete data, the obvious next question followed almost immediately. How could such an immense region of emptiness have formed in a universe governed by the laws of physics as we know them? Galaxies not placed at random. They are born out of the collapse of matter, guided by invisible scaffolding made of dark matter, shaped by fluctuations that were present from the very beginning. If those processes are universal, why do they sometimes leave behind cavities so vast that they almost feel like mistakes? To answer this, we need to start with the earliest moments of the universe. In the very beginning, matter and energy were spread almost evenly. The cosmic microwave background, which is a snapshot of the universe 380,000 years after the Big Bang, shows this near uniformity clearly. The temperature of that background radiation is nearly the same everywhere, varying by only 1 part in 100,000. Those slight variations, however, were enough to set the stage for everything that followed. Tiny regions that were slightly denser than average became seeds for galaxies and clusters. Regions slightly less dense became the beginnings of voids. Gravity amplified these differences. Over billions of years, denser regions pulled in more matter, becoming filaments and clusters. Emptier regions lost matter to their neighbours, becoming increasingly vacant. In principle, this process should naturally create voids. But most simulations suggest those voids are not usually hundreds of millions of light years wide. The Booty's void pushes the limits of what standard models predict. That is the puzzle. One possibility is that the void is not truly a single empty bubble, but rather the overlap of several smaller voids that merged. Just as soap bubbles can join together to form one larger cavity, cosmic voids may combine over time. If that is the case, then the Booty's void is not an exception to the rules, but an extreme outcome of them. It would still be rare, but not inexplicable. Another explanation involves the role of dark matter. Dark matter outweighs ordinary matter by a factor of about 5 to 1. Its gravitational pull is what causes galaxies to form in the first place. If the distribution of dark matter in the early universe was especially uneven, that could create regions where almost no galaxies form. A patch of the universe with lower than average dark matter density might naturally evolve into a void like Booty's. In this view, the void is not a mystery, but a reflection of the underlying dark matter landscape. But even with these ideas, the scale of the Booty's void remains unusual. In many simulations, voids of 100 or 150 million light-years are common, but reaching 300 or more is rare. This has led some scientists to wonder whether our models of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, might need refinement. Inflation stretched tiny quantum fluctuations into the seeds of structure. If inflation had small irregularities, certain regions could have ended up unusually underdense. The Booty's void might then be a fossil from that earliest moment, a relic of how inflation played out in our patch of the cosmos. The puzzle also invites creative thinking. Some researchers have considered whether the void might contain matter that is difficult to detect. Could there be diffuse gas, faint dwarf galaxies, or other subtle structures hidden within? Surveys have found a few galaxies inside the void, but far fewer than expected. If there are more faint objects we cannot yet see, that might explain some of the discrepancy. Advances in telescopes and instruments may one day reveal whether the void is truly as empty as it appears, or whether we are simply missing its faintest residents. There is also the question of perspective. When astronomers map the cosmic web, they do so from one vantage point: Earth. Our observations are always subject to limitations of angle, depth, and sensitivity. Could the void appear larger than it is because of how we are measuring it? As surveys improve, with deeper catalogues and wider coverage, the picture becomes clearer, and while refinements may change its exact dimensions, the Buddhist void remains an extreme outlier no matter how you measure it. In grappling with this puzzle, scientists often return to analogies. They compare the universe to a landscape shaped by hills and valleys. Galaxies gather in the valleys where gravity pulls matter together. Voids are the hills, regions left high and dry. If the hills are small, the valleys are numerous and rich. If the hills are large, the valleys are fewer and deeper. The Buddhist void is like an enormous plateau in this analogy, a region so high above the average that almost nothing could settle there. The puzzle deepens when you consider how voids evolve over time. As the universe expands, matter flows out of voids into denser regions. This process should make voids larger and emptier as time goes on. But the rate of this expansion depends on the balance between gravity and dark energy, the mysterious force driving the acceleration of the universe's expansion. In that sense, voids become natural laboratories for testing these fundamental forces. If the Buddhist void is unusually large, it may offer clues about how dark energy and gravity have interacted across cosmic history. For example, some studies suggest that the growth of voids can help constrain the properties of dark energy. If dark energy is stronger, voids expand more quickly. If it is weaker, they expand more slowly. Measuring voids of different sizes, therefore, becomes a way of probing the invisible. The Buddhist void, by being so large, presses this test to the extreme. Does its size fit with what we expect given our current understanding of dark energy? Or does it hint at something more complex? That is part of the ongoing puzzle. But puzzles in science are not failures. They are opportunities. Each time something doesn't fit neatly into our models, it forces us to refine them. The Buddhist void has done just that, pushing cosmologists to think harder about initial conditions, dark matter, dark energy, and the growth of structure. It has become both a challenge and a guide, showing us where our theories need to stretch. There is also the possibility that the void is not special at all, but simply an extreme case of randomness. In any large enough system, improbable events occur. Toss a coin 1,000,000 times, and you will occasionally get 100 heads in a row. Build a universe with billions of regions, and you may occasionally get one enormous void. Perhaps the Buddhist void is just that, the cosmic equivalent of a long streak of heads. If so, the puzzle is not why it exists, but why we are so surprised. Still, the surprise is real. Scientists are used to voids, but not this large. The Buddhist void is a reminder that even well-established theories can produce results that stretch our sense of normal. It keeps cosmology honest, reminding us that nature is under no obligation to be tidy. The puzzle of how such voids form also has a human side. When we imagine the universe, we tend to picture abundance, stars, galaxies, nebulae, clusters. To discover that it also contains vast deserts is unsettling. The Buddhist void confronts us with the reality that emptiness is as much a part of the cosmic story as fullness. The puzzle, then, is not only scientific but psychological. Why do we find emptiness harder to accept than presence? Why do we assume the universe should be evenly filled when it clearly is not? In the end, the Buddhist void is both a mystery and a lesson. It may be the product of rare initial conditions, the overlap of smaller voids, the influence of dark matter, or the subtle fingerprints of cosmic inflation. It may be all of these at once. Its puzzle is not a single question with a neat answer, but a set of interconnected mysteries that force us to look deeper. And perhaps that is the point. The void exists because the universe is not simple. It is not uniform, not predictable in every detail. It is structured, textured, and varied. To understand how such voids form is to understand how the cosmos itself has evolved from its first moments to now. And that journey, like the void itself, stretches farther than we can easily imagine. When astronomers try to explain why the Buddhist void exists, they inevitably find themselves talking about something they cannot see. It is not the galaxies that tell the whole story, nor the gas, nor the light we can detect with even our most sensitive instruments. It is the hidden matter that outweighs everything visible, the dark matter that makes up most of the structure of the universe. Without dark matter, galaxies would never have formed, voids would never have deepened, and the cosmic web itself would not exist. If the Bootes void is a puzzle, then dark matter's fingerprints are all over it. Dark matter is one of the most unsettling ideas in modern science, precisely because it resists direct detection. We know it exists not because we see it, but because we see its effects. Galaxies spin faster than they should, as if held together by invisible mass. Clusters of galaxies bend light more strongly than their visible matter accounts for, a phenomenon called gravitational lensing. The cosmic microwave background shows patterns that require dark matter to explain. Everywhere we look, the evidence piles up that about 85% of the matter in the universe is invisible to us. Ordinary matter, the atoms that make up stars, planets, and people, is just a small fraction. If dark matter is the scaffolding of the cosmos, then its distribution determines where galaxies form and where they do not. The Bootes void, then, is not simply an accident of visible matter, but a reflection of an underlying emptiness in the dark matter web. If the region started with a lower than average density of dark matter, then galaxies would have been starved from the very beginning. Over billions of years, as matter flowed toward denser regions, the underdense area would have become emptier still, expanding into the vast void we see today. To imagine this, think of a landscape where valleys and hills guide the flow of water. Rain falls everywhere, but it collects in valleys, forming rivers and lakes. The hills remain drier, with only small trickles running down. In the same way, dark matter provides the valleys and hills of the universe. Galaxies collect in the valleys, while the hills remain nearly barren. The Bootes void is like a vast plateau, high enough that little matter ever gathered there. Its scale is immense, but the principle is the same. The invisible fingerprints of dark matter can even be traced in the shapes of the galaxies that do exist within the void. Because they are so isolated, they often preserve more of their original structure. In denser regions, galaxies collide, merge, and distort one another. But in a void with fewer neighbours, galaxies spin more quietly, retaining their form for longer. Their rotation curves, the way stars orbit at different distances from the centre, reveal the influence of dark matter halos. By studying these lonely galaxies, astronomers can test how dark matter shapes them without the confounding effects of constant collisions. In that sense, the void becomes a kind of cosmic laboratory, where the fingerprints of dark matter are easier to isolate. Gravitational lensing provides another clue. When light from distant galaxies passes near clusters of dark matter, it bends. By mapping these distortions, astronomers can infer the presence of dark matter, even if it is otherwise invisible. In voids, the lensing signal is weaker, as expected, because there is less mass. But the pattern of weakness itself is telling. By measuring how weak the lensing is in a region like the Bootes void, scientists can estimate just how underdense it truly is. The absence of a strong signal is itself a kind of fingerprint, a silent signature of the dark matter that isn't there. Dark matter's role also extends to the earliest moments of cosmic history. During inflation, tiny quantum fluctuations were stretched to enormous scales. Where those fluctuations created overdensities, dark matter gathered, leading to filaments and clusters. Where they created underdensities, dark matter was sparse, leading to voids. In this way, the Bootes void may be a direct imprint of quantum fluctuations from the first instant of time. If that is true, then the void is not just an empty region, but a message from the birth of the universe, encoded in the absence of matter. The fact that we can even contemplate such a connection between quantum ripples smaller than atoms and voids hundreds of millions of light years wide is one of the most astonishing aspects of modern cosmology. Yet dark matter remains elusive. We still do not know what it is made of. Candidates range from weakly interacting massive particles or WIMPs to axions to sterile neutrinos. Despite decades of searches, no direct detection has been confirmed. Underground detectors, particle accelerators, and astrophysical observations all hunt for its nature. In the meantime, we study its fingerprints, the patterns it leaves in galaxies, clusters, and voids. The Bootes void, by its very existence, adds to that evidence. Whatever dark matter is, it must be something that allows regions like this to form. Its fingerprints are written into the very emptiness. One fascinating possibility is that the properties of dark matter might influence the size of voids. If dark matter particles are cold, meaning they move slowly compared to the speed of light, then they clump on small scales, leading to a web with many small filaments and voids. If dark matter is warm, moving faster, then structure forms more smoothly, with fewer small clumps and larger voids. In this way, the Bootes void could help distinguish between different theories of dark matter. Its size and shape may be telling us something fundamental about the nature of the unseen majority of the universe. The fingerprints of dark matter are also found in the way galaxies move at the edges of voids. As matter flows out of underdense regions into denser ones, galaxies at the boundaries feel a gentle push. Their velocities record this motion, like leaves drifting on currents. By measuring these flows, astronomers can map the gravitational landscape shaped by dark matter. The Bootes void is one of the most dramatic examples of this, its immense emptiness driving surrounding galaxies outward, carving its boundaries more sharply. For people outside the scientific community, the idea that invisible matter shapes the largest structures of the universe can be hard to accept. But the evidence is overwhelming. Without dark matter, galaxies would not hold together. Without it, filaments and walls would not form. Without it, voids like Bootes would not exist. It is the unseen architect, leaving fingerprints everywhere we look. The Bootes void is not an exception, but a showcase of its work, a gallery where absence itself becomes a clue. There is a certain irony in this. We study galaxies because they shine, because they give off light that travels across billions of years to reach us. Yet what defines their arrangement, what sculpts the cosmic web, is the matter that does not shine. We see only the tips of the iceberg. The true structure lies beneath, hidden but real. The Bootes void, in all its vast emptiness, is one of the clearest reminders of this truth. Its very lack of galaxies forces us to confront what we cannot see. The invisible fingerprints of dark matter are not limited to cosmic scales. They are present in our own galaxy, in the way the Milky Way spins, in the way stars orbit farther out than visible mass can explain. They are present in the way clusters hold together, in the way light bends as it passes them. They are everywhere, silent, shaping without shining. To talk about the Bootes void is to talk about dark matter, because without it, such a void could not exist. And so, as we drift through this immense emptiness in our imagination, we are not really drifting through nothing. We are drifting through the unseen, through a landscape shaped by invisible hands. Dark matter's fingerprints are everywhere, written into the galaxies that are missing, the light that is bent, the structures that rise and fall. The Bootes void is not just a hole in the map. It is a message from the invisible majority of the universe, a reminder that what we cannot see may be even more important than what we can. To understand why a place like the Bootes void exists at all, we have to step back, far back, to a time before galaxies, before stars, even before atoms. We have to consider the universe in its infancy, in the first fractions of a second after the Big Bang. It was in those earliest moments that the seeds of everything we see today were planted. And strangely enough, the vast emptiness of the Bootes void may be one of those seeds stretched across space and time by a process we call cosmic inflation. Cosmic inflation is a theory born from the need to explain puzzles about the universe that ordinary expansion alone could not solve. Observations of the cosmic microwave background, that faint afterglow of the Big Bang. show that the universe is astonishingly uniform on large scales. Temperatures are nearly identical in every direction, even though those regions were never in contact with each other in the early universe. How could such uniformity exist without some kind of process to smooth it all out? Inflation was proposed as the answer. According to the theory, in the tiniest fraction of a second after the Big Bang, the universe underwent a period of expansion so rapid that it defies everyday comprehension. Space itself grew exponentially, doubling in size again and again in less than a heartbeat. In that brief interval, quantum fluctuations, tiny random variations in energy, were stretched to cosmic proportions. They became ripples in the density of matter, the blueprint from which galaxies, clusters, filaments, and voids would eventually form. The universe we see today, with its web of structures and vast empty spaces, is a fossil record of those ancient ripples. Where the fluctuations made regions slightly denser, matter clumped together under gravity, leading to the luminous filaments and walls of galaxies. Where they made regions slightly less dense, matter flowed out, leaving behind voids. The Boots void, in this view, is not just an accident of later evolution. It may be the direct descendant of one of those primordial ripples, a region that began underdense and grew emptier with time. To imagine this, think of a pond struck by raindrops. Each drop creates ripples, overlapping and combining into patterns. In the early universe, inflation magnified such ripples on a cosmic scale. Over billions of years, gravity amplified them further. The patterns we see in the distribution of galaxies are the frozen waves of that ancient rain. The Bootis void is one of the troughs, an especially deep one, carved by the combined effect of many ripples. This connection between the smallest scales of physics and the largest scales of cosmology is one of the most astonishing aspects of modern science. Inflation takes quantum fluctuations, variations at scales smaller than atoms, and stretches them into features hundreds of millions of light-years wide. The emptiness of the Bootis void may therefore be a relic of quantum uncertainty itself, a reminder that the fabric of reality is built on randomness magnified to cosmic proportions. Inflation also explains why voids are not evenly distributed. The ripples were not identical everywhere. Some regions were denser, some emptier. Over time, this led to the lumpy web-like structure of the universe. Without inflation, the distribution would be far smoother, and the Bootis void would be inexplicable. With inflation, it becomes not just possible but inevitable that some regions would be unusually empty. The Bootis void is an outlier, yes, but outliers are part of the pattern when randomness is stretched on such a grand scale. The cosmic microwave background gives us a way to test this idea. Satellites like COBE, DOLMAP and Planck have measured its fluctuations with extraordinary precision. The faint variations in temperature across the sky, only millionths of a degree, match the predictions of inflation. They show a spectrum of ripples that align with the structures we see today. The voids, filaments, and clusters are all written into that pattern. The Bootis void, although not directly visible in the microwave background, is consistent with the idea that inflation seeded regions of emptiness as well as abundance. Some scientists even suggest that studying voids could provide new insights into inflation itself. The exact properties of inflation, how long it lasted, what drove it, whether it was a single smooth process or something more complicated, remain unknown. By examining extreme structures like the Bootis void, we may learn more about those earliest moments. If voids are larger or more numerous than predicted, that could indicate something unusual about inflation. Perhaps it was not perfectly uniform. Perhaps it involved multiple fields or transitions that left their mark on the cosmos. The void becomes not just a curiosity but a probe of the universe's birth. There is also the matter of scale. Inflation did not just make the universe larger, it made it unimaginably larger. The part of the universe we can observe, about 93 billion light-years across, may be only a tiny patch of the whole. Inflation could have created regions far beyond our view, each with its own pattern of ripples. The Booty's void, then, is a feature of our local cosmic neighbourhood, but it hints at a grander reality. If inflation produced voids here, it produced them elsewhere as well, scattered across the vastness beyond what we can see. And yet, inflation is still a theory. It is supported by strong evidence but not directly proven. Other explanations for the structure of the universe exist, though none match the data as well. The Booty's void, by being so large, tests the theory. It asks whether inflation alone is enough to explain it, or whether something more is at play. Could there be physics beyond inflation that shape such extremes? Could dark energy, or modifications to gravity, have amplified the void? These are open questions, and the Booty's void sits at their intersection. For the human imagination, the connection between inflation and voids is almost surreal. The emptiness of a region hundreds of millions of light-years wide may trace back to a fluctuation smaller than an atom, stretched by expansion beyond comprehension. It is a reminder of how deeply the universe is interconnected, how the tiniest details can echo across the larger scales. When we gaze into the Booty's void, we are not just looking at a patch of space that lacks galaxies. We are looking at the shadow of quantum fluctuations magnified by inflation, preserved for billions of years in the silence between galaxies. This way of thinking also reframes our sense of normal. If voids are natural products of inflation and gravity, then emptiness is not a mistake, but a fundamental feature. The Booty's void may feel unsettling, but it is part of the blueprint. It is there because inflation created variety, because randomness ensures that not every region is the same. The universe is not a smooth, uniform canvas. It is textured, rippled, uneven, and that unevenness began in the first instant of time. As we continue to study voids, we're not just learning about cosmic geography. We're reaching back to the origins of everything. Inflation took fractions of a second and imprinted them onto billions of years. The Booty's void is one of those imprints, stretched across space like a fossil from the beginning. Its scale is vast, but its roots are delicate, quantum ripples frozen into place by the expansion of space itself. And so, the role of inflation is not just to explain why galaxies exist where they do, it is to explain why absence exists too. The Booty's void is an absence with a history that begins in the smallest fluctuations of energy, carried outward by the greatest expansion the universe has ever known. It is a silence that began in the earliest moments, amplified until it became one of the largest structures we can observe, and in that silence we can still hear the echo of the beginning. When people hear the word void, it's natural to imagine a place that is truly empty, a hollow sphere of pure nothingness stretching across space. But the Booty's void is not quite that absolute. It is extraordinarily sparse, yes, far more than the average regions of the cosmos, but it is not perfectly vacant. If it were, it might not have been detectable at all. What makes it striking is the balance. Almost nothing, but not quite. When astronomers first measured it, they expected tens of thousands of galaxies within its volume. Instead, they found only a few dozen. The difference between expectation and reality is what gave it its reputation as one of the most desolate regions of the observable universe. And yet, even in that desolation, there are galaxies. They are faint, isolated, lonely, but they are there. Their very presence is important because it reminds us that voids are not absolute. They are relative. They are places where the density of matter is far below average but not zero. Think of deserts on Earth. The Sahara, for example, appears empty when you fly over it. From above you see dunes, sand, rocks and little else. But if you look closely, life is there. Sparse, adapted, tenacious. Tiny lizards burrow beneath the sand. Insects cling to bits of shade. Plants anchor themselves in the dry soil. The Booty's void is similar in concept. To the cosmic eye, it looks barren. But if you look closely, you find a handful of galaxies living quiet lives, isolated in the vast darkness. One of the most remarkable things about those galaxies is their isolation. In dense regions, galaxies constantly interact. They collide, merge, and exchange material. These interactions shape their evolution, driving bursts of star formation or altering their structure. But in a void, such interactions are rare. A galaxy can spend billions of years without a close encounter. This makes void galaxies a special kind of laboratory. They show us what galaxies look like when left mostly alone, when their growth and behaviour are guided by internal processes rather than external nudges. Some void galaxies appear to be smaller and less developed than their counterparts in clusters. Others retain higher amounts of gas, suggesting that without the disruptive influence of neighbours, they have conserved more of their raw material for star formation. There is even evidence that some void galaxies rotate differently, preserving angular momentum that might otherwise have been disturbed in crowded environments. In short, they carry a different history, one shaped by quiet isolation rather than constant jostling. Astronomers who study void galaxies often describe them as blue and faint, meaning they are still forming stars but at a slower rate. They are not the grand spirals or massive ellipticals you see in clusters. They are modest, almost humble, quietly existing in places where the odds seem stacked against them. In a way, they resemble small towns in the middle of a vast countryside, thriving in their own slower rhythm, untouched by the bustle of cities. It is tempting to imagine what the sky would look like from a planet inside one of those galaxies. To the naked eye, the stars within the galaxy would appear just as they do here. The night sky would still be full of constellations, planets, nebulae, and perhaps the glow of a Milky Way-like band of stars. But when telescopes turned outward, beyond the boundaries of the host galaxy, the difference would be dramatic. Instead of hundreds of galaxies visible in deep exposures, there might be only one or two faint smudges. The realization that there is almost nothing else would be overwhelming. Civilizations there would likely have an entirely different story about the universe, shaped not by abundance but by scarcity. This is where the phrase, almost nothing but not quite, takes on deeper meaning. It emphasizes how much difference those few galaxies make. Without them, the Booty's void would be featureless, perhaps even impossible to identify in the same way. With them, it becomes not just emptiness, but emptiness, punctuated by tiny lights. Those lights matter because they tell us about survival in extreme conditions, about how galaxies can still form and persist even where the odds are poor. The galaxies inside the void also challenge our understanding of structure formation. How did they form there at all? If the region was underdense from the beginning, why did any matter clump enough to create them? The answer lies in the fact that underdensity is not absolute. Even in a void, there are small fluctuations. Those fluctuations can gather enough material to form galaxies, though fewer and more faint than elsewhere. It's a reminder that the universe is not binary, full or empty, all or nothing. It exists on a spectrum, with voids still containing traces of presence. In cosmology, this balance is crucial. If voids were perfectly empty, it would be hard to reconcile them with our models of matter distribution. The fact that they still contain galaxies, even a few, fits better with the idea that they are natural outcomes of initial conditions. The Booty's void is extreme, but it is not an impossible break from the rules. Its almost nothing status is what keeps it consistent with the broader picture of cosmic evolution. The presence of galaxies in the void also has philosophical weight. There is something profound about the idea that even in the most barren regions of the cosmos, life persists in some form. Not life in the biological sense necessarily, but life in the sense of activity, of stars forming, of galaxies spinning. The void is not absolute silence. It is a hushed room where a few faint voices still speak. Those voices may be quiet, but they matter. They prove that the universe is rarely, if ever, truly empty. It also reframes how we think about emptiness in general. People often equate voids with nothingness, but science shows us that nothing is a slippery concept. Even the vacuum of space is not truly empty. It teems with quantum fluctuations, with particles appearing and disappearing, with a faint hum of background radiation. The Bootis void looks empty on a grand scale, but on closer inspection it too is filled, not abundantly, but enough to remind us that the universe resists total absence. When scientists describe the void as underdense, they mean that its density of matter is a fraction of the cosmic average. If the universe is like a city with an average population density, the Bootis void is a rural county with only a handful of houses spread across vast land. The comparison helps put the idea into perspective. Emptiness is relative. For astronomers used to seeing thousands of galaxies per volume of space, a region with only a few dozen is strikingly empty. But it is not void in the literal sense. That distinction also matters when we talk about how voids evolve. Over time, as matter flows out of them into denser regions, they become emptier. But they never become completely bare. Some galaxies remain, some gas lingers, some faint structures persist. The Bootis void, despite its reputation as a cosmic desert, is still home to galaxies, still part of the web. It is not cut off, not excluded, but integrated into the larger pattern of the cosmos. And perhaps this is the deeper lesson of almost nothing, but not quite. It tells us that absence is never absolute. Even in the most extreme voids there is something. Even in the places we call empty, faint traces endure. The Bootis void may be the largest desert we know, but deserts too are landscapes with their own life, their own rhythms, their own presence. The galaxies that survive there are like reminders that the universe always leaves a trace, always resists complete silence. From a scientific standpoint, those faint galaxies are important data points. From a human standpoint, they are symbols of persistence. They show us that emptiness is not the end of the story, but part of it. The Bootis void is not nothingness. It is almost nothing, but not quite. And in that not quite, an entire layer of meaning unfolds. If the Bootis void is a cosmic desert, then the few galaxies inside it are like wandering travellers who never found the busy trade routes, who instead drift quietly in solitude. They are not surrounded by rich neighbourhoods of thousands of companions. They do not collide often, nor do they live in the bustling intersections of filaments where gravity pulls galaxies together. They are stray galaxies, marooned in one of the emptiest places known to science, drifting alone in a sea of darkness. Astronomers have catalogued only a few dozen galaxies inside the Bootis void. By comparison, in a region of similar size outside the void, we would expect thousands upon thousands. These galaxies are special not because they are unusual in their composition, but because of where they are. Their environment shapes their history. A galaxy inside a cluster might be stripped of gas by the hot plasma that fills the cluster's core. It might collide and merge with neighbours, growing in mass and transforming its shape. But inside the void, these processes happen rarely, if at all. The galaxies there evolve in isolation, slowly, quietly, with little interference. This isolation makes them fascinating test cases for astronomers. In the crowded universe, it is difficult to tell how much of a galaxy's shape and behaviour comes from internal processes versus external interactions. In the void, the noise of outside influence is lower. Studying these galaxies helps us understand what galaxies do when left to themselves, without the constant push and pull of neighbours. Some of the galaxies found inside the void appear small, faint and blue. This means they are still forming stars, but at a relatively modest pace. They have not grown into giant ellipticals or massive spirals like the Milky Way. Instead, they resemble dwarf galaxies or modest disks, carrying on their lives without dramatic transformation. In dense regions, galaxies might form stars in great bursts triggered by collisions. Void galaxies, by contrast, seem to form stars steadily, drawing from their reservoirs of gas at a gentle pace. Other galaxies inside the void are more unusual. A few appear elongated, stretched out as though spinning in relative peace for billions of years. Without tidal forces from neighbours to disrupt them, their shapes remain intact, preserving clues about how they formed in the first place. These galaxies offer insights into the angular momentum of galaxies in general, showing what happens when the initial conditions of formation are not constantly disturbed. To think about their loneliness, imagine standing on a beach at night looking across the water. If you were in a coastal city, you might see dozens of lights from ships, towns, or other signs of life across the bay. But if you are on a remote island, the horizon may be dark with only a single light flickering in the distance. That is the view of a galaxy inside the void. The cosmic horizon is empty, with only the faintest hints of other galaxies glimmering far away. For an astronomer living in such a galaxy, the discovery of the broader universe would be delayed, perhaps even impossible without extraordinary technology. The loneliness would not just be physical, but existential. This is one reason why the Buddha's void captures imagination outside the scientific community. It is not just the emptiness that fascinates, but the idea of lonely galaxies adrift within it. We instinctively empathize with isolation. We imagine what it would be like to exist in such solitude. Even though galaxies are not conscious, the metaphor resonates with us. Stray galaxies become symbols of persistence in an environment defined by absence. From a scientific perspective, their presence also reassures us. If the void were truly empty, it would be far harder to explain. The fact that a few galaxies do exist there shows that even in the most underdense regions, gravity and matter can still gather enough to form structures. They may be faint and scattered, but they are proof that the processes of galaxy formation are universal. The void suppresses them, but it does not erase them. There are practical challenges to studying these galaxies. They are faint, and the distances involved make them hard to observe in detail. But new instruments and surveys are beginning to change that. The Sloan Digital Sky Survey and other projects have mapped void galaxies with increasing precision. Future telescopes, like the Vera C. Rubin Observatory, with its legacy survey of space and time, promise to reveal more. Each new detection adds to the picture, showing us how galaxies survive in near solitude. One interesting finding is that void galaxies may contain more neutral hydrogen gas than average. This gas is the raw material for star formation. In crowded environments, galaxies often lose their gas through interactions, or through the harsh conditions of clusters. In voids, however, the gas remains, allowing galaxies to continue forming stars slowly over time. This makes them intriguing objects for studies of long-term galactic evolution. They may provide a glimpse of how galaxies looked in the early universe, before collisions and interactions became common. There is also the question of dark matter halos. Every galaxy is thought to sit within a halo of dark matter, which provides the gravitational glue holding it together. Void galaxies may retain especially pristine halos, undisturbed by mergers. Studying their dynamics could offer cleaner tests of dark matter models, stripping away the complications introduced by constant galactic interactions elsewhere. Once again, the void turns out to be a laboratory, sparse, but valuable precisely because of that sparseness. The few galaxies inside the Boots void are not spread evenly. They appear to cluster slightly, forming small groups within the vast emptiness. Even in a desert, oases sometimes occur. These small groups may reflect regions where density was just high enough to allow multiple galaxies to form together. But the distances between those groups are still immense. Travelling from one to another would take far longer than between galaxies in a filament or wall. The loneliness remains. For those who think philosophically about the universe, these stray galaxies are almost haunting. They remind us that isolation is part of the cosmic story. Not every galaxy is part of a bustling cluster. Some drift in silence, unseen by almost all others, and yet they persist. Their stars burning, their planets circling, their gas clouds slowly collapsing into new generations of suns. If there is life in such a galaxy, it would grow up in a cosmos that feels nearly empty. The night sky would look much the same, but the sense of being surrounded by billions of other galaxies would not exist. their worldview would be profoundly different from ours. In a way, this thought experiment underscores how much our place shapes our knowledge. We live in a relatively crowded region of the cosmic web, surrounded by galaxies we can see with modest telescopes. That abundance gave us the data to build cosmology as a science. If we lived in the Bootes void, the science might be far behind, our understanding of the universe far more limited. These stray galaxies drifting alone remind us that perspective is everything. Where you stand in the universe influences what you can know, and so the Bootes void is not a pure nothingness. It is a near nothing punctuated by a few stray galaxies, each carrying its own history. They drift alone, but their loneliness is instructive. They show us what galaxies become without constant interference. They reveal how structure forms even in the least likely places, and they remind us that even in the greatest deserts of space presence persists. In that sense, the void is both empty and full, empty of abundance, but full of meaning. The stray galaxies drifting alone are like whispers in a quiet room, faint but unmistakable. They tell us that the universe is never completely silent, never entirely bare. Even in its emptiest places, it leaves traces of structure, of persistence, of light. It is one thing to map the Bootes void on paper, to measure its size in light years and describe it in terms of galaxies missing from its volume. It is another thing entirely to imagine what it would mean to live there. The thought experiment is both humbling and unsettling, for in such a place the experience of the universe would be profoundly different. The view of the night sky, the course of scientific discovery, even the philosophy of life would shift in ways we can only speculate about. Let us begin with the most immediate experience, the sky above. From the surface of a planet orbiting a star inside one of the few galaxies in the Bootes void, the view would, at first, seem familiar. The galaxy itself would look much the same as ours. Stars would shine, planets would orbit, nebulae would glow faintly in the distance. The Milky Way's broad band of stars across the sky would have its equivalent there too, a swath of light made up of billions of suns bound together by gravity. To the naked eye, the difference would not be obvious. A being looking up would still see a glittering canvas of stars. But the difference would emerge when telescopes came into play. In our own galaxy, even the earliest telescopes revealed more than stars. They uncovered nebulae, and eventually astronomers discovered that many of those nebulae were galaxies themselves, far beyond the Milky Way. Deep sky images taken with modest equipment today reveal hundreds of galaxies in a single frame. In the Bootes void, those frames would come back nearly empty. Where we see dozens of companions crowding the field of view, they would see only one or two faint smudges. The overwhelming impression would be not of a crowded universe, but of isolation. This isolation would profoundly affect the course of science. Imagine a civilization developing astronomy in such an environment. They would notice stars, of course, and perhaps recognize that those stars moved in relation to each other, hinting at their placement within a galaxy. But would they ever guess that other galaxies existed at all? With so few visible, the leap to the idea of a vast universe filled with billions of galaxies might take much longer, perhaps millennia longer, than it did for us. Even with advanced telescopes, the galaxies beyond their own would be faint whispers of light. The conclusion might easily be that they were alone, a single island in an endless sea. This would shape philosophy as much as science. For us, the realization that there are billions of galaxies has shifted our perspective on existence. We are one among many, a small part of a vast community of cosmic structures. In the void, the opposite lesson would be drawn. The sense of uniqueness, even of solitude, would be overwhelming. Civilizations might grow up believing they were the sole example of galactic life, the only structure of their kind in the cosmos. The psychological impact of such a worldview would be hard to overstate. It would influence myths, religions, sciences, and perhaps even the will to explore. The scale of exploration itself would also be altered. In our corner of the universe, Neighbouring galaxies are millions of light years away, still unreachable by any current or foreseeable technology, but close enough to be detected and studied. In the Booty's void, those neighbours would be vastly farther. The distance between galaxies there is far greater than in crowded regions. Even if a civilization developed the ability to travel across intergalactic space, the journey would be lonelier and longer. The ocean between islands would stretch almost without end. Exploration would mean confronting not just difficulty, but overwhelming emptiness. And yet, in some ways, life inside a void galaxy might feel ordinary. A star is a star, wherever it is. A planet circling it could still support oceans, mountains, and skies. Intelligent beings there might build homes, dream dreams, and wonder at the stars above without ever realizing how unusual their situation is. For them, the void would not feel empty. It would feel normal. They would know nothing else. The sense of isolation is, in a way, our projection, based on our knowledge of the broader universe. For them, solitude would simply be the background condition of existence. Still, once the truth was discovered, the shock would be immense. Imagine the moment when astronomers in such a galaxy finally detect a faint smudge of light and realize it is another galaxy, unimaginably far away. Then, another. Slowly, the picture forms that their galaxy is not alone but surrounded by an almost unfathomable emptiness, with only a few distant companions scattered across the horizon. The realization that they are adrift in one of the largest voids in the universe would be staggering. To discover that not only are they not central, but they are in fact in one of the most desolate corners of existence, would be a revelation unlike any other. It is possible that this knowledge might inspire despair. To know that the rest of the universe is far away, unreachable and densely populated compared to their lonely patch could feel isolating. But it could also inspire awe. The very fact of survival in such a sparse place would be remarkable. Their galaxy would be a beacon in the dark, a rare survivor in a desert of nothingness. That rarity could become a source of meaning, a story of resilience told across generations. From the standpoint of physics, life in such a galaxy would also mean subtle differences in environment. The lack of frequent galactic interactions could shape the properties of the galaxy itself. There might be less disturbance in the orbits of stars, fewer massive bursts of star formation triggered by collisions, a calmer pace of evolution overall. The stars and planets might exist in quieter neighbourhoods, less prone to the chaos of crowded clusters. If life depended on stability, perhaps void galaxies would offer more of it. Loneliness might be the price of peace, but the isolation would come with costs. Heavy elements, the building blocks of planets and life, are often spread through the universe by supernovae and galactic collisions. In regions with fewer interactions, the distribution of those elements might be slower or less widespread. Planets might be rarer. Chemistry might take longer to build complexity. If so, civilizations in voids might be less common than those in crowded regions, or slower to develop. The emptiness could shape not just their worldview, but their very existence. On a more human level, thinking about what living there would be like reveals how much our own place has shaped us. We live in a galaxy that is part of a filament, surrounded by neighbours, close enough to study them and learn that we are not alone. That knowledge has expanded our imagination. It has given us humility and wonder. If we had grown up in the Booty's void, our imagination might have been narrower, our humility less sharp, our wonder shaped by the belief that we were singular. The truth of our location has written itself into our culture. Living in the void would have written a very different story. And yet, the void is part of the same universe as the rest. Life there, if it exists, would be subject to the same laws of physics, the same chemistry of stars, the same potential for planets and oceans. The difference would be in perspective. To live there would be to live with silence where we see abundance, with distance where we see community. It would be a life shaped by emptiness, but not defined entirely by it. For even there, stars shine, planets orbit, and galaxies persist. When we imagine living in the Buddha's void, we are really imagining how different our sense of place could be. We are asking how much our worldview depends on our environment, and how much it might change if that environment was stripped of abundance. The answer seems clear. It would change everything. Science, philosophy, exploration, meaning itself would all be reframed. The void is not just a physical feature of the universe. It is a thought experiment in perspective, a reminder that our knowledge is always shaped by where we stand. When people first heard about the Buddha's void in the early 1980s, the scientific description alone was enough to stir curiosity. A region hundreds of millions of light years across, containing almost no galaxies, stood out like a scar on the map of the universe. But the fascination that followed was not limited to scientists. The idea of such a vast emptiness reached beyond astronomy journals and into popular culture, philosophy, and even casual conversation. The void became more than a discovery. It became a symbol, and that is because emptiness has always held a peculiar power over the human imagination. On one level, the appeal is simple. The universe is usually thought of as overflowing with abundance. Billions of stars, billions of galaxies, planets, nebulae, supernovae, a cosmos bursting with activity. Against that backdrop, the Buddha's void feels like an exception, an unsettling absence in a place where presence is expected. Humans notice patterns, but we notice the gaps just as strongly. A silent pause in a piece of music can feel more powerful than the notes surrounding it. A blank patch in a painting draws the eye as surely as the painted sections. Likewise, a void in the map of the universe captures attention because it is a silence in the cosmic symphony. On another level, there is the psychological weight of emptiness itself. Across cultures and histories, humans have been both attracted to and unnerved by emptiness. Deserts, oceans, and skies have all played this role on Earth. They are spaces defined not by what is present, but by what is absent. They inspire awe, but also fear. They are places of imagination, where myths are born because the mind tries to fill what the senses cannot. The Buddha's void is like a cosmic desert, and it taps into that deep-seated reaction. When people hear that a region of space so large contains so little, the imagination rushes to fill it, with speculation, with stories, with meaning. Science itself often provokes awe when it confronts us with extremes. Black holes, neutron stars, supernovae, all of these are examples of nature pushing limits. But emptiness pushes limits in a different way. Instead of overwhelming presence, it is overwhelming absence. The idea that there could be a place so empty, so devoid of galaxies, resonates because it feels alien. It challenges our intuition that the universe should be evenly filled. We expect to find something everywhere we look. The Buddha's void denies that expectation, and that denial becomes intriguing. The void also resonates because of how it interacts with human stories of isolation. Loneliness is a theme as old as storytelling itself. Myths of exiles, tales of wanderers, and reflections on solitude appear in every culture. When astronomers describe lonely galaxies drifting inside the void, it mirrors those themes. The galaxies become characters in an imagined story, cast away from the crowded centres, surviving in silence. People project themselves into that narrative, imagining what it would be like to live in such isolation. The void becomes a stage on which human emotions are reflected, even though it is a purely physical phenomenon. There is also the matter of scale. Numbers like 300 million light-years stretch beyond comprehension, but when tied to emptiness, they gain a haunting quality. To imagine that vastness filled with galaxies is difficult enough, but to imagine it almost empty is stranger still. The mind struggles to grasp the enormity, and in that struggle, imagination takes over. People picture endless darkness, silent expanses, cosmic deserts. The void becomes not just a scientific object, but a canvas for the imagination to paint upon. Writers, Journalists and artists quickly seized upon the boot's void after its discovery. Some described it as a hole in the universe, others as a cosmic scar. Some speculated about what might hide inside: alien civilizations, massive structures, phenomena unknown to physics. The absence itself became an invitation for invention. Where science admitted emptiness, imagination supplied presence. That interplay between knowledge and speculation is part of why the void endures in popular thought. For scientists, the void is fascinating because it tests theories. For non-scientists, it is fascinating because it speaks to something more primal, the tension between fullness and emptiness, presence and absence. We are accustomed to filling space, whether with sound, with objects, or with meaning. When confronted with silence, we wonder what it hides. The boot's void captures imagination precisely because it is a silence on a scale so vast that it cannot be ignored. It also intersects with broader philosophical themes. In philosophy, emptiness has often been a subject of reflection. In some traditions, emptiness is seen as a source of peace, a space for contemplation. In others, it is a source of dread, a reminder of nothingness. The Buddha's void can be seen both ways. Some interpret it as unsettling, a reminder of cosmic indifference. Others see it as calming, a vast stillness that puts human concerns into perspective. In either case, it engages imagination not through what it contains, but through what it refuses to contain. The fascination deepens when you consider the possibility of life. For us, the knowledge that we're surrounded by billions of galaxies makes the universe feel teeming with potential. The odds of life elsewhere seem favourable. In the void, those odds feel different. A civilization living there would look outward and see emptiness. The possibility of neighbours would feel remote. When people imagine that scenario, they project human emotions onto it. Loneliness, curiosity, longing. The void becomes a thought experiment in existential philosophy. What does it mean to live in a universe that feels empty? How does perspective shape meaning? Even scientists are not immune to this imaginative pull. While they analyse the void with equations and simulations, they too sometimes describe it in terms of metaphor. They call it a desert, a hole, a bubble. These words reveal not just scientific accuracy but human need. We reach for familiar metaphors to make sense of the unfamiliar. In doing so, we reveal that the void is not just an object of study, but a mirror for the human mind. And perhaps that is the most important reason the void captures imagination. It reminds us of our limits. We cannot easily comprehend its size. We cannot fully explain its origin. We cannot directly experience its emptiness. Confronted with those limits, imagination steps in. The boot's void forces us to think not only about the universe, but about ourselves, about how we react to absence, about how we fill silence with story. It is likely that as science advances, we will learn more about voids, refining our understanding of how they form and evolve. But their imaginative power will not fade. Just as deserts, oceans, and skies still inspire wonder, despite our knowledge of them, the Buddha's void will continue to capture imagination simply by being what it is, a vast stretch of space where almost nothing exists. The scale and emptiness ensure that it will remain a symbol, not just a scientific fact. In the end, the void captures imagination because it sits at the intersection of science and story. It is a measurable, real structure of the universe, but it is also a metaphor waiting to be filled. It speaks to our fascination with extremes, with silence, with solitude, with the unknown. And as long as humans wonder about the universe, the boot's void will be one of the places where wonder gathers, not because of what is there, but because of what is not. Whenever humans encounter something vast and strange, we tend to fill the gaps with stories. The boot's void, being one of the largest and emptiest structures ever found, was destined to provoke speculation from the moment it was discovered. For scientists, it was a problem to be solved, a feature of the cosmic web that needed explanation. For the broader imagination, it became a canvas. What could such an emptiness hide? Why would the universe allow a gap so immense? If nature leaves a silence, our minds instinctively compose something to fill it. Almost immediately after its discovery in 1981, ideas about alien civilizations began to cluster around the Boots void. Some speculated that the void was not natural at all, but the result of advanced beings who had done something to clear it out. Science fiction writers in particular seized on the possibility. Perhaps the void was carved by alien technology, a region where civilizations had dismantled galaxies for energy, or where matter had been consumed by colossal engineering projects. The sheer size of the void lent itself to these imaginings. A region 300 million light-years across almost demands explanation, and for many, aliens were the most tantalizing answer. Others took the myth-making in a different direction. They imagined the void as a kind of forbidden zone, a cosmic scar where something catastrophic had happened in the distant past. Perhaps it was the site of an ancient battle between civilizations, or a place where the universe itself had glitched, leaving a hole in its fabric. These ideas were not scientific, but they were compelling stories, born from the human need to explain what feels inexplicable. The void also played into existing myths of nothingness and silence. Across cultures, emptiness has often been seen as a liminal space, a place of transition or danger. Deserts, oceans, and the night sky have all been treated as realms where the ordinary rules do not apply, where spirits, gods, or mysteries dwell. The Booties void, described in simple terms as a hole in the universe, tapped directly into that ancient imagery. It felt like a modern myth, a place so strange that it seemed destined to hold secrets. Even mainstream media occasionally leaned into these stories. Articles about the void sometimes used dramatic language, calling it a great hole or a cosmic desert. Television specials speculated about what might lurk inside. In popular imagination, the void became a mystery not just of science, but of existence, a reminder that the universe still contains places that feel uncanny. From a scientific standpoint, of course, there is no evidence for aliens or cosmic scars. The void is consistent with our understanding of how matter distributes itself under the influence of gravity and dark matter. It is rare but not impossible, and yet the stories persist. They persist because they tap into something deeper than science. They speak to our need for narrative, for filling silence with meaning, for seeing mystery where explanation is sparse. This is not unique to the Booties void. Throughout history, humans have spun myths around emptiness. Sailors once imagined sea monsters lurking in uncharted oceans. Travellers in deserts told tales of mirages and spirits. The night sky itself was filled with constellations, stories imposed on the void between stars. The Booties void is simply a new frontier for this old habit. Faced with a cosmic emptiness, we imagine what might hide inside. The idea of aliens in particular is irresistible. In a universe with billions of galaxies, the possibility of life elsewhere is tantalizingly real, even if we have no proof. Linking that possibility to the largest emptiness we know makes for a powerful story. Some writers suggest that the void is quiet because civilizations have not reached it, or because they avoid it. Others imagine it as a hiding place, a region where advanced beings could operate unseen. The fact that no evidence supports these ideas does not diminish their allure. On the contrary, the lack of evidence makes them feel more open to speculation. There is also the unsettling thought that the void could represent the end of civilizations. Some have proposed, half seriously, that the void looks empty because something destroyed the galaxies that once occupied it. A cosmic catastrophe, an unknown physics, or even an intelligence on a scale beyond comprehension. These ideas are not scientific, but they are stories that reflect human fears. The void becomes a stage for our anxieties about isolation, destruction, and the limits of knowledge. At the same time, the void inspires myths of wonder rather than dread. Some imagine it as a place of hidden beauty, where phenomena beyond our understanding occur, where new laws of physics operate, or where creation itself might begin anew. In this sense, the void becomes not a scar but a womb, a place of possibility. The emptiness is reimagined as potential, as a blank canvas waiting for meaning. What unites these myths is the human response to silence. We are uncomfortable with absence, so we fill it with narrative. The Buddhist void, being one of the greatest absences we know, naturally attracts some of the grandest narratives. It becomes a mirror for our hopes, fears, and curiosities. In the same way that people once mapped monsters onto the edges of the known world, we now map stories onto the edges of the known universe. From one perspective, these myths might seem like distractions from science, but in another sense they are companions to it. They show that the void captures not just data but imagination, not just observation but story. Science explains how the void formed, why it exists, and what it contains. Imagination asks what it might mean. The two are not opposed, but complementary. Together they make the void more than a number in a paper. They make it a part of human culture. Even among scientists, the void sometimes takes on a mythical quality. When they describe it as a hole in the universe, or a cosmic desert, they are using metaphors as much as measurements. Those metaphors help communicate the scale and strangeness of what has been found. They also reveal that even the most rational minds are drawn to the mythic pull of emptiness. The void is not just data, it is a story waiting to be told. In the end, aliens, myths, and stories of cosmic nothingness are not about the void itself so much as about us. They show how we respond to absence, how we project meaning onto silence, how we grapple with scales beyond comprehension. The Buddhist void is a real feature of the universe, measurable and explainable. But it is also a canvas for the imagination, a place where science and story meet. And perhaps that is fitting, for the universe is not only made of galaxies and stars, but also of the stories we tell about them, the meanings we attach, the myths we weave. The void, in all its emptiness, gives us space for those stories to grow. The way the Buddhist void is usually described as a massive hole in the universe, hundreds of millions of light years across with only a scattering of galaxies, can give the impression that it is truly empty, a region stripped bare of matter. But that impression is not quite correct. It is emptier than almost anywhere else we know, but to call it empty would be misleading. The universe rarely offers pure nothingness. Even in the largest voids there is always something, if you know where to look. When astronomers map the Buddhist void, what they are really measuring is galaxy density. In the same volume of space where thousands of galaxies should exist, only a few dozen are found. That makes it extraordinarily underdense compared to the cosmic average. But galaxies are not the whole story. Between them lies gas, plasma, dark matter, and radiation, some visible and some not. The void may be sparse, but it is not truly barren. Cosmologists prefer to use the term underdense rather than empty. This is an important distinction. It means that the density of matter inside the void is lower than the universal average, but not zero. Ordinary matter, dark matter, and even dark energy still permeate it. The difference is that their distribution is unusually thin. The void is less a hole and more a thinning, a region where the cosmic fabric stretches wider than normal. Consider the cosmic microwave background, the faint afterglow of the Big Bang. Its photons pass through the void on their way to us. If the void were truly empty, those photons would travel unaffected. But in fact, their journey is influenced subtly by the low-density environment. Scientists can measure these effects, such as the integrated Sachs-Wolf effect, which shows how cosmic voids alter the energy of passing photons. The Buddhist void leaves fingerprints not by what it contains, but by how it alters the light that moves through it. That tells us immediately that it is not a perfect nothingness. It still has gravitational effects, still participates in the cosmic dance. dark matter is a key part of this. Even in the Booty's void, dark matter is present, though less than elsewhere. The invisible scaffolding that defines the universe's large-scale structure does not vanish inside the void. It thins out, becoming weaker, but it is still there. Without it, the few galaxies that do exist inside the void could not survive. Their halos depend on the gravitational pull of dark matter. Even emptiness, it turns out, has structure beneath the surface. Gas too may be present in small amounts. Observations of other voids suggest that faint, diffuse hydrogen gas flows through them, too thin to form stars easily but still part of the intergalactic medium. Detecting this gas is difficult, but hints of it have been found. The Booty's void may contain long, tenuous filaments of such gas, invisible to most telescopes but real nonetheless. If so, then the void is not an absolute desert, but a place where matter exists in ghostly form, spread too thin to shine. Even galaxies themselves are not absent. As noted earlier, astronomers have catalogued dozens inside the Booty's void, though far fewer than expected. These galaxies tend to be faint, small, and isolated. They are not grand spirals like the Milky Way, nor massive ellipticals like those in clusters. Instead, they resemble modest dwarfs, quietly forming stars at a slow pace. Their very survival proves the void is not completely hostile. Even in such underdense conditions, galaxies can form and endure. The question of whether the void is really empty also depends on perspective. Compared to the bustling filaments of the cosmic web, it is shockingly bare. Compared to true vacuum, it is not bare at all. It still contains matter, energy, radiation, and structure. The contrast is what makes it striking. It is not nothingness, but less than average. The human mind gravitates to extremes, so we call it empty. But the reality is subtler. It is not a hole in the universe, but a thinning of its texture. This distinction matters because it helps us understand what voids are and how they evolve. Voids expand as matter flows out of them toward denser regions, pulled by gravity. But they never empty completely. Their underdensity increases, but they always retain some matter. This means voids are not static features but dynamic ones, growing and changing over time. The Booty's void is not frozen in place. It has evolved for billions of years and will continue to do so, becoming emptier but never fully empty. Another aspect to consider is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is thought to be uniformly distributed, permeating all of space. That means the Booty's void is filled with it, just like any other region. If dark energy dominates the cosmos, as most evidence suggests, then in a strange way the void is no less full of it than any crowded cluster. Emptiness, therefore, is relative. Even where galaxies are missing, the fabric of the cosmos remains, stretched and infused with unseen energy. Some astronomers even argue that voids like Booty's are essential to understanding dark energy. Because voids are underdense, they expand faster than the universe as a whole. By studying their growth, scientists can test how dark energy behaves. The Booty's void, with its extreme scale, becomes a natural laboratory for this purpose. It may look empty, but in its expansion lies valuable information about the fundamental forces of the cosmos. There is also the subtle question of what we mean by real. If emptiness is defined as a lack of galaxies, then yes, the Booty's void is empty. If it is defined as a lack of matter and energy altogether, then no, it is not empty at all. Our language struggles with this nuance. We like clear categories, but the universe resists them. The void exists in between, neither full nor vacant, but something in between. For human imagination, this ambiguity is part of the appeal. Calling it empty makes it mysterious, dramatic, almost frightening. Knowing it is not truly empty grounds it in science, but also adds depth. The Booty's void is not a hole carved out of reality. It is a feature of reality itself, a region shaped by the same forces that made galaxies elsewhere, simply pushed to an extreme. It is emptiness with texture, absence with presence, and perhaps that is the deeper truth. The Booty's void is really empty only if we define fullness narrowly, in terms of bright galaxies. If we widen our definition to include dark matter, gas, radiation, and energy, it is not empty at all. It is thin, sparse, ghostly, but not void in the absolute sense. To call it empty is to simplify, to emphasize its contrast with crowded regions. But to study it carefully is to see that even emptiness has layers. So the answer to whether the Booty's void is really empty is both yes and no. Yes, compared to the universe at large, it is astonishingly underdense. But no, compared to the concept of true nothingness, it is still full. It is filled with the unseen, the faint, the quiet. It is not a hole, but a hollow, not a scar, but a thinning. It is almost empty, but not quite. And in that distinction lies its meaning. When we hear about a place like the Booty's void, the numbers alone are enough to impress us. 330 million light-years across, only a few dozen galaxies where thousands should be. But beyond the statistics, there is another layer, one that belongs less to astronomy and more to psychology. Emptiness is not just a physical fact, it is an experience. And when people encounter the idea of emptiness on such a scale, the response is deeply human, a mixture of awe, unease, curiosity, and contemplation. Emptiness has always carried a psychological weight. In daily life, we encounter it in smaller forms: a quiet room after a long conversation, an empty street late at night, a vast landscape without a single human figure. These experiences can feel peaceful, but also eerie. They draw attention to absence, to the fact that something we expect is missing. Multiply that feeling by a scale beyond imagination, and you begin to sense what the Booty's void evokes. It is a silence not of a moment, but of hundreds of millions of light years. One reason emptiness affects us so strongly is that we are pattern-seeking creatures. Our minds are tuned to notice presence, faces, voices, movement, objects. When those patterns vanish, when silence replaces sound and blankness replaces form, we instinctively react. Some interpret it as calm, others as fear, but the intensity is shared. The Booty's void taps into that instinct. It is not just an absence of galaxies, it is an absence of pattern, a place where the expected order of the universe drops away. This sense of absence carries philosophical weight as well. Humans have long wrestled with the concept of nothingness. Is nothing truly possible, or is it always a kind of something in disguise? Philosophers in different traditions have framed emptiness as either a threat or a liberation. Some saw it as the void that underlies existence, a reminder of mortality and the limits of knowledge. Others saw it as peace, as openness, as potential. The Booty's void revives these debates in a modern context. It is not an abstract nothingness, but a physical one, mapped by telescopes and described in data, and yet its meaning still feels philosophical. There is also the simple fact that emptiness magnifies scale. When you look at a crowded star field, the mind struggles to comprehend abundance, but when you look at emptiness, the mind measures scale by the absence itself. The lack of galaxies over hundreds of millions of light years creates a different kind of vertigo. It is not a dizzying abundance, but a dizzying lack. The imagination stretches to fill the silence, and in doing so, it feels the immensity more sharply. For many people, that immensity provokes unease. The idea that there are regions of the universe so barren can feel unsettling. It raises questions about isolation, about insignificance, about what it means to exist in a cosmos where emptiness is as real as fullness. The psychological weight of the void is the weight of realizing that not everything in the universe is teeming with life and light. Some places are profoundly still, and that stillness echoes in our own fears of loneliness, silence, and death. Yet for others, the void brings comfort. To imagine such vast emptiness is to place our concerns in perspective. Compared to hundreds of millions of light years, the scale of our daily worries feels small, almost negligible. The void becomes a meditation, a reminder of how much bigger reality is than the problems that preoccupy us. In this way, emptiness is calming. It clears the mind the way a blank canvas clears space for thought. The Buddhist void, in its silence, becomes not a threat but a relief. This duality is what gives emptiness its power. It can terrify or soothe, depending on how it is framed. When described as a whole, it may inspire dread. When described as a desert, it may inspire awe. When described as a thinning of matter, it may inspire curiosity. The psychological weight is not fixed but shaped by perception. And in that sense, the Buddhist void is as much a mirror of the mind as it is a feature of the universe. The weight of emptiness also appears in art and culture. Painters have long used negative space to create meaning, leaving parts of the canvas blank to draw attention to what is there. Musicians use silence in the same way, creating tension or calm between notes. Writers leave pauses, gaps, or ellipses to emphasize absence. The Buddhist void is like a cosmic version of these techniques. It is negative space on the largest canvas imaginable. And just as in art, the emptiness is not nothing. It is part of the composition. For those who reflect on it more personally, the void raises questions about human solitude. Are we, like those galaxies drifting in the emptiness, essentially alone? Is our place in the cosmos one of connection, surrounded by others, or one of isolation, separated by vast distances? The void seems to embody both truths at once. It shows that isolation is possible, even natural, and yet it also shows that persistence is possible too. Galaxies survive in the void, faint but real. They remind us that even in isolation, existence continues. The psychological weight of emptiness is not just about fear or wonder, it is also about responsibility. When confronted with the idea of such vast absence, some feel a deeper appreciation for the presence we do have. The stars above us, the galaxies around us, the life on Earth, all become more precious when contrasted with the silence of the void. Emptiness heightens our awareness of fullness. The Buddha's void in its starkness makes the Milky Way feel even more remarkable. At the same time, the void challenges our assumptions about the universe as a whole. We are used to thinking of space as filled with galaxies, as crowded with stars. The Buddha's void reminds us that emptiness is just as real, just as fundamental. The psychological weight comes not only from scale, but from surprise, from the fact that the universe does not conform to our expectations. It is stranger, more varied, and more uneven than we imagined. And perhaps this is why the Buddha's void lingers in our imagination. It is not just a place on a map. It is confrontation with absence, a reminder of silence, a meditation on nothingness. Its psychological weight is the weight of realizing that the universe contains not only presence but absence, not only sound but silence, not only light but shadow. The void is a balance, and in that balance we find both fear and peace. The Buddha's void tends to capture the most attention, partly because of its immense size and partly because of its striking name. But it is not alone. The universe is filled with voids, and though most are smaller, they are no less intriguing. To place the Buddha's void in context, it helps to know about these other cosmic deserts, to compare their scales and features, and to understand how they fit together to form the cosmic web. One of the first voids to be mapped in detail is the local void. This is the underdense region closest to us, bordering the local group of galaxies that includes the Milky Way, Andromeda, and their smaller companions. The local void is not as large as Bootes, measuring on the order of tens of millions of light-years across, but it has a direct impact on our galaxy. Observations show that the Milky Way itself is moving relative to the cosmic background radiation, partly because the local void is pushing us outward, while denser regions like the Virgo cluster are pulling us in. In this way, voids exert influence not only by their emptiness, but by the flows of matter they create around them. The local void is a reminder that we live next to a desert, even as we dwell within a relatively rich filament of galaxies. Another notable void is the Eridanus supervoid. This region drew particular attention because it appears to line up with a mysterious feature in the cosmic microwave background known as the cold spot. The cold spot is an area of the sky where the background radiation is slightly cooler than average. Some scientists have proposed that the Eridanus supervoid, measuring hundreds of millions of light-years across, might be responsible. As photons from the microwave background pass through such a large underdense region, their energies can be altered, creating the appearance of a colder patch. The exact connection is still debated, but the Eridanus supervoid remains one of the most studied examples of how emptiness can influence observations on the larger scales. In the constellation of Sculptor lies another vast region of low density known as the Sculptor void. This one is notable because it surrounds a large-scale filament of galaxies called the Sculptor wall. The contrast between the rich wall of galaxies and the sparse void beside it is striking. It demonstrates clearly how the universe is structured like foam, dense sheets and filaments enclosing great hollows. The Sculptor void may not be as famous as Boots, but it is an important part of the cosmic web that defines our local universe. Then there is the KBC void, named after its discoverers Keenan, Barger and Cowie. This void, which some researchers propose may include our own galaxy near its centre, is a controversial subject in cosmology. The idea is that the Milky Way sits within a region of space that is slightly underdense compared to the universal average, extending hundreds of millions of light-years. If true, this would mean our measurements of cosmic expansion could be subtly biased by our location. The KBC void has been invoked to explain discrepancies in measurements of the Hubble constant, the rate at which the universe expands. While the debate continues, the possibility that we ourselves are inside a large void is a reminder that emptiness is not just far away, it may surround us. Beyond these, there are countless other voids catalogued by galaxy surveys. The Sloan Digital Sky Survey and other large-scale mapping projects have revealed a cosmic geography filled with voids ranging in size from 20 to a few hundred million light-years. Each void is unique in detail but similar in principle. Regions where galaxy density is far below the average. Together they account for the majority of the universe's volume. That is perhaps the most startling fact of all. Voids may look like exceptions, but they are not rare. In fact, they are the rule. Most of space is void, with galaxies strung along filaments and walls like beads outlining bubbles. This realization reframes the Bootes void. It is not an isolated oddity, but an extreme example of a common feature. If the cosmic web is like a sponge, then voids are its holes, and the Bootes void is one of the largest. But every hole matters. Each void plays a role in shaping how galaxies cluster, how matter flows, and how the universe evolves. Studying one void helps us understand them all. The study of voids as a class has even become its own subfield in cosmology. Researchers analyze their statistics, distributions, and properties to test theories of dark matter and dark energy. Voids are sensitive indicators of cosmological parameters. Because they expand faster than average regions, they act as amplifiers of the effects of dark energy. By comparing voids of different sizes and ages, scientists hope to measure the properties of that mysterious force more precisely. In this sense, the Bootes void is not just a curiosity, but part of a much larger toolkit for probing the universe. From a human perspective, the sheer number of voids is sobering. When we imagine the universe, we often picture galaxies upon galaxies stretching endlessly. But in reality, most of that stretch is emptiness. The galaxies are the exceptions, the beads along threads. The voids are the background. To understand the universe is to understand not just the luminous presences, but the dark silences. The Bootes void is only the loudest of those silences. It is also worth noting that voids are not evenly distributed. Some regions of the cosmic web are riddled with small voids, others dominated by a few large ones. Their variety tells us about the history of structure formation. Smaller voids often merge into larger ones over time, like soap bubbles joining together. The boot's void may be the result of many smaller voids overlapping, creating one enormous cavity. Other famous voids may be younger, smaller, or shaped by different dynamics. In comparing them, scientists trace the evolution of the universe itself. In popular imagination, the Booty's void overshadows its peers because of its size, but knowing about the others enriches the picture. The local void shows that emptiness is near us, influencing our motion. The Eridanus supervoid shows that voids can leave imprints on the cosmic microwave background. The Sculptor void shows how voids and walls contrast sharply in cosmic structure. The KBC void shows that even our measurements of cosmic expansion may depend on whether we live inside a void. Each tells a different story, and together they remind us that voids are not rare anomalies but fundamental elements of the cosmos. The presence of so many voids also deepens the psychological effect. If there were only one Booter's void, it might feel like an odd curiosity, an exception to the rule of a full universe. But knowing that voids dominate the cosmic volume changes the narrative. The universe is not mostly galaxies sprinkled evenly across space. It is mostly emptiness, with galaxies outlining the edges. Presence is the exception. Absence is the rule. This inversion of expectation is part of why voids fascinate us so deeply. In reflecting on these other voids, we come to appreciate the Booty's void not as an isolated wonder, but as the grandest example of a pattern repeated across the universe. It is famous because it is extreme, but it belongs to a family of structures that define the very shape of reality. To study one is to study all, and to imagine their scale together is to realize that we live in a universe built as much from emptiness as from matter, a universe where silence is not the absence of the song, but part of its rhythm. When astronomers describe the Booty's void, they focus on its physical properties, its size, its sparseness, the handful of galaxies scattered across its interior. But for anyone who hears about it, the impression goes beyond measurements. The idea of such a vast emptiness presses on deeper questions. Questions not only of science, but of meaning. What does it mean that the universe contains spaces so barren? What does it say about existence itself that nothingness, or near nothingness, takes up most of reality? One of the most striking lessons the Booty's void teaches is that absence is not accidental. It is part of the architecture of the universe. Galaxies, filaments, and clusters may seem to be the main story, but they exist because emptiness exists beside them. Matter flows into dense regions precisely because other regions are underdense. The universe is a balance between presence and absence, between abundance and scarcity. Without the voids, there would be no clusters. Without emptiness, there would be no structure. The Booty's void makes that point clearer than almost any other place. It shows that what is missing is as important as what is there. This lesson extends beyond cosmology. In our lives too, absence plays a role as real as presence. Silence gives shape to music. Space gives shape to architecture. Pauses give meaning to speech. The void reminds us that nothingness is not meaningless. It is part of the pattern. The Booty's void, stretched across hundreds of millions of light years, is like a cosmic example of this truth. It teaches that absence can be structural, not just incidental. It also teaches humility. When we look at galaxies, we see abundance, and abundance makes us feel that we belong to a universe overflowing with light. But the Booty's void reminds us that the universe is not built for our comfort. It is not arranged to reassure us. It is vast, uneven, and often silent. Our place within it is fortunate. We live in a galaxy within a filament surrounded by neighbours. But that is not the only kind of place there is. Other regions are lonelier. Other galaxies live in near solitude. Existence does not guarantee fullness. Sometimes it guarantees emptiness. That realization humbles us, showing that our experience is not the universe's default, but one of its many possibilities. There is also a lesson about scale. Humans naturally think in terms of what we can see and touch. Rooms, cities, planets. These are the scales that feel real. Even galaxies, though far away, can be pictured as large islands of stars. But the Buddha's void stretches those scales until they almost break. To imagine hundreds of millions of light years of emptiness is to confront limits of comprehension. In that confrontation, we learn something about existence itself, that it is larger than we can grasp, and that our understanding will always be partial. The void does not diminish us. It expands us, forcing us to stretch imagination to its limits. Another lesson comes from the persistence of galaxies inside the void. They are few, but they exist. Against overwhelming odds, matter still clumped together, stars still formed, light still shines. Their survival teaches that existence is resilient. Even in the most underdense regions, life of a kind continues. That resilience is a metaphor for our own. We too exist in conditions that could easily have been hostile, but here we are. The void teaches not only emptiness, but persistence. The Buddhist void also raises questions about uniqueness. Civilizations, if they exist inside void galaxies, would grow up with a very different view of the universe. Their philosophy, science, and culture would be shaped by isolation. They might believe themselves to be alone, not just in their galaxy, but in all of existence. We, by contrast, live in a region where galaxies are plentiful and visible. Our understanding of the cosmos is shaped by abundance. The void shows that existence is relative. Where you are shapes what you know, and what you know shapes what you believe. It reminds us that reality is not uniform, and neither are the perspectives within it. The void also touches on the concept of nothingness in philosophy and religion. Some traditions treat emptiness as a threat, a reminder of mortality and the fragility of life. Others treat it as a source of peace, a clearing where awareness can rest. The Buddha's void embodies both views at once. It is terrifying in its scale, a reminder that most of the universe is silent, but it is also calming, a vast expanse where nothing presses, nothing intrudes. It shows that emptiness is not one thing but many, capable of carrying dread and serenity at the same time. From a scientific angle, the void teaches that our models must always account for extremes. Theories that explain average cases are not enough. They must explain the rare, the outliers, the anomalies. The Buddhist void is such an anomaly. It pushes our theories of structure formation, inflation, and dark matter to their limits. In doing so, it forces us to refine them. Existence, the void teaches, is not tidy. It includes the rare as well as the common, the vast as well as the small. To understand it, we must be ready for surprises. There is also a subtler lesson. The Buddhist void reminds us that discovery itself is shaped by absence as much as by presence. When astronomers mapped the sky and noticed the void, what caught their attention was not what was there, but what was missing. The absence became the discovery. In life, too, absence can reveal truths that presence conceals. We often focus on what is visible, but sometimes it is what is missing that matters most. The void embodies this paradox. It is a place defined by galaxies that are not there. Its reality is absence, and yet that absence teaches us as much as any presence. On a more personal level, the void prompts reflection about our place in the cosmos. Are we defined by the fullness of our world, or by the emptiness that surrounds it? Do we take comfort in abundance, or do we learn humility from scarcity? The Buddhist void suggests that both are part of existence. To live in the universe is to live between abundance and absence, between filaments and voids. The cosmic web itself is built from this balance. We are not outside of it. We are within it, shaped by it. The void also hints at the possibility that nothingness is as fundamental as somethingness. In physics, quantum fields permeate space, fluctuations occur even in vacuums, and dark energy fills every corner. Absolute nothingness may not exist at all. What we call voids are really just thinnings, relative absences. The Buddhist void teaches us that nothingness is never pure, but always relative. Even emptiness is textured. Even absence has structure. That lesson reframes how we think about existence. It is not a simple binary of being or not being. It is a spectrum, with voids as one extreme. Finally, the Buddhist void teaches us about wonder. Science often explains mysteries, turning the unknown into the known. But sometimes, explanation deepens mystery rather than resolves it. The Buddhist void is such a case. We can describe why it exists, how it fits into the cosmic web, what it tells us about dark matter and inflation. And yet, its scale, its silence, its emptiness still provoke awe. That awe is itself a lesson. Existence is not diminished by explanation, it is enriched. The more we learn, the more we realize how much remains beyond comprehension. The void teaches us that knowledge and wonder are not opposites, but partners. In all these ways, the Buddhist void speaks not only to cosmology, but to existence itself. It reminds us that absence can be structural, that humility is necessary, that resilience persists even in emptiness, that perspective shapes belief, that nothingness is relative, and that wonder endures. It is a lesson written across hundreds of millions of light years of near nothingness, a silence that speaks louder than many presences. In contemplating it, we learn not just about the universe, but about ourselves. When we speak of the Buddhist void, we begin with numbers, because the numbers are staggering. Hundreds of millions of light years across, fewer than 100 galaxies where thousands should be, the kind of scale that defies imagination. But by the time we've sat with the idea long enough, the numbers give way to something else, a feeling, an atmosphere, an encounter not only with astronomy, but with the meaning of emptiness itself. It's not only about the maps we've drawn of the cosmos, but about how we as human beings respond when we're asked to contemplate so much silence. For some, the idea of the void feels like a confrontation. To know that there are regions of the universe so barren, so devoid of the structures we've come to expect, can feel heavy. It can remind us of loneliness, of distance, of how fragile our own place is within the cosmic web. We're used to finding comfort in presence. Stars filling the night sky, galaxies crowding deep exposures, the reassuring hum of life around us. The void removes that comfort. It is a reminder that not every part of the universe is abundant. Some places are defined by absence. That realization has weight. And yet, as we sit with it longer, another feeling emerges. Emptiness has its own kind of beauty. The Buddhist void is vast, but its vastness is not hostile. It is quiet, and that quiet can be calming. There is comfort in the idea that not all of existence is crowded and noisy. There are places where silence reigns, where the universe breathes out, leaving room. In a world where our lives are often full of movement and noise, the very concept of such an expanse of calm becomes soothing. The Buddhist void reminds us that the universe contains stillness as well as activity, silence as well as sound. This comfort grows when we recognize that emptiness is never absolute. The void is not truly empty. It contains galaxies, faint and scattered, but real. It contains dark matter, diffuse gas, and the ever-present fabric of space itself. Even in the largest desert there are oases. Even in the greatest silence there are whispers. This balance is reassuring. It tells us that the universe does not allow complete nothingness, only gradations of absence. The void is not an erasure of existence, but a thinning of it. That distinction softens the unease, turning fear into contemplation. The Buddhist void also teaches us to appreciate what we have. When we realize that most of the universe is emptiness, the fact that we live in a galaxy surrounded by others becomes all the more remarkable. Our view of the night sky, filled with stars and framed by the glow of the Milky Way, is not inevitable. It is a privilege of location. We dwell in a region where abundance is visible. Knowing that other regions are lonely highlights the richness of our own. The void, in its silence, makes our own presence feel brighter. There is another kind of comfort too, the comfort of perspective. Our lives are filled with concerns that feel overwhelming, responsibilities, struggles, uncertainties. When we place those concerns against the backdrop of hundreds of millions of light years of emptiness, their weight shifts. They do not vanish, but they shrink into scale. The void whispers that the universe is larger than any one worry, more enduring than any one problem. It offers perspective not through noise, but through silence. That perspective can be grounding, even healing. The comfort of nothingness is also found in the way it allows space for thought. Just as silence in music creates room to feel the notes, emptiness in the universe creates room for reflection. The Buddha's void is like a pause written into the cosmos, a reminder that not everything is filled, that there are intervals of space where nothing intrudes. For those who encounter it, it can become a kind of meditative image, an invitation to rest within the vastness rather than to fear it. Even scientifically, the void offers comfort of a kind. It reassures us that the universe has order. The Buddha's void may feel extreme, but it is not inexplicable. It is the outcome of known processes, of fluctuation stretched by inflation, of matter flowing into denser regions, of dark matter shaping structure. The void fits within the pattern, and that knowledge is calming. It tells us that even silence belongs to the design, even absence is part of the whole. In the end, the Buddha's void shows us that existence is not only about what is present, but about what is absent too. Its comfort lies in reminding us that balance is everywhere. Without voids, there would be no filaments. Without silence, there would be no sound. Without pauses, there would be no rhythm. The universe is not made only of galaxies, but of the spaces between them. To accept that is to find peace in the emptiness as well as in the fullness. As we let this idea settle, the void becomes less a place of dread and more a place of calm. It becomes a cosmic reflection of something we already know in our own lives, that emptiness can be frightening at first, but it can also be restful. That silence can feel like loneliness, but it can also feel like peace. That nothingness can be overwhelming, but it can also be comforting. The Buddha's void contains all of these truths at once, stretched across a scale almost beyond comprehension. And perhaps the deepest comfort comes from realizing that even in the greatest emptiness, there is still something. Galaxies still drift there. Light still travels through it. Space itself still exists. The universe never allows complete nothingness. The Buddha's void is almost nothing, but not quite. And that not quite is everything. It is the thread of persistence, the reminder of survival, the echo of presence within absence. To know that even the most barren desert of the cosmos is not truly empty is to know that existence endures everywhere, in every form. So when we think of the Buddha's void, we can think not only of scale and sparseness, but of comfort. Comfort in silence. Comfort in perspective. Comfort in the balance between presence and absence. Comfort in the reminder that even the greatest emptiness is still part of existence, still connected to everything else. The void is not a hole torn in the universe. It is a feature of the universe, as real as galaxies and stars. Its comfort lies in showing us that nothingness is not an end, but a part of the whole. And as we drift back from that vast silence in our imagination, we can carry that comfort with us, into our own lives, into our own quiet moments, into the spaces between our own thoughts. For the Buddha's void is not only out there, mapped in telescopes and charts, it is also within us, a reminder that emptiness and presence live side by side, and that both can be beautiful. As we leave the Buddha's void behind, the silence of that immense desert lingers, like a faint echo in the mind. It reminds us that the universe is not only a story of stars and galaxies, but also of the spaces between them, the pauses that give structure to the song. If you found this time together soothing, you might want to return, to drift again into these cosmic reflections. You can stay connected here, where we wander slowly through the mysteries of science, not to solve them all, but to rest with them, to let them become companions as we fall towards sleep. So thank you for listening, for sharing this journey into one of the quietest corners of the cosmos. May the vast calm of the Buddha's void travel with you into your own stillness tonight, wrapping you gently in the comfort of nothingness.